The universe is a boundless ocean of mystery, and right in our cosmic backyard, the local group of galaxies, there are secrets lurking that defy everything we think we know. Picture this, scattered across millions of light years, hidden among the swirling arms of Andromeda, the Triangulum galaxy, and our own Milky Way, lie 50 objects so bizarre, so utterly inexplicable, they challenge the very limits of our understanding. Some glow with energies that shouldn't exist, others move in ways that break the laws of physics, and a few might just be something entirely unknown to science. This isn't science fiction. These are real cosmic anomalies waiting to be unraveled, and today we're diving deep into their enigmas. What if I told you that one of these objects could be a remnant of a civilization so advanced their technology appears to us as pure magic, or that another might be a natural phenomenon so rare it's only happened a handful of times in the entire history of the universe? The local group, our galactic neighborhood, is home to wonders that make black holes and supernova look ordinary by comparison. These 50 strange objects aren't just curiosities. They're cosmic puzzles begging to be solved, each one a whisper from the far reaches of space, hinting at truths we've yet to grasp. This journey isn't just about listing strange sights in the cosmos. It's about venturing into the unknown, where every discovery raises more questions than answers. Think of it like stumbling upon a locked chest in the depths of space. Each object we examine is another intricate key, another piece of the grand puzzle. Some might rewrite the rules of astrophysics, others could force us to reconsider our place in the universe, and who knows, one of them might even hold the clue to a question we haven't thought to ask yet. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Let's start with the elephant in the cosmic room, Andromeda's dark matter halo. This colossal structure, invisible to telescopes yet massive enough to warp space itself, holds a mystery that's baffled scientists for years. See, every galaxy has a dark matter halo, but Andromeda's is different. It's not just bigger, it's denser, heavier, and strangely lopsided, as if some unseen force sculpted it into a shape that defies our models. Imagine tossing a pebble into a pond and seeing the ripples freeze mid-motion. That's how jarring this discovery is for astrophysicists. Here's why it matters. Dark matter is the cosmic glue holding galaxies together, and its distribution should follow predictable patterns. But Andromeda's halo is like a fingerprint smudged by something we can't see. Some theories suggest it's gorged on smaller galaxies, cannibalizing their dark matter over billions of years. Others whisper about exotic particles or even flaws in our understanding of gravity itself. The most tantalizing clue, the halo's asymmetry. It's thicker on one side, like a shadow stretched by a light we can't locate. Could this be evidence of a long-ago collision with another galaxy, or a sign of dark matter behaving in ways we've never imagined? What's at stake isn't just a puzzle about Andromeda, it's a challenge to the rulebook of how galaxies form. If we're wrong about dark matter here, what else might we have missed? Every observation peels back another layer, revealing just how much we still don't know about the invisible scaffolding of the universe. Andromeda's halo isn't just a curiosity, it's a cosmic riddle, and solving it could rewrite the story of everything. While Andromeda's dark matter halo defies expectations with its sheer strangeness, the Triangulum galaxy holds a mystery of a different kind, one that's eerily silent. At the heart of this spiral galaxy lies a supermassive black hole, but unlike the violent, energy-spewing monsters we're used to, this one is almost meditative. Most galaxies, including our own Milky Way, host black holes that occasionally flare up, devouring nearby stars and blasting jets of radiation across space. Triangulum's black hole, though, sits in near-total stillness, barely making a whisper in the cosmic noise. This silence is more than just odd, it's a challenge. Supermassive black holes are supposed to be loud, They are surrounded by swirling disks of superheated gas, screaming their presence across the electromagnetic spectrum. But Triangulum behaves like a ghost, refusing to feast even when surrounded by plenty. Scientists have a few theories. Maybe it's starving, its surroundings picked clean by some ancient catastrophe. Or perhaps it's in a state of deep hibernation, biding its time before an inevitable awakening. The most intriguing possibility, it might simply be too small. Most black holes of its kind grow by merging with others, but Triangulum could be a rare example of one that stayed close to its original size, never gaining the mass to roar like its cousins. Then there's the chilling alternative. What if we're missing something fundamental? Black holes are supposed to follow certain rules, but this one's defiance hints that our playbook might be incomplete. Could there be entirely new states of black hole behavior we've never accounted for? Or is Triangulum's silence a clue to some deeper cosmic rhythm, a lull in a cycle we don't yet understand? The quieter it stays, the louder the questions become. Unlike the chaos of Andromeda's halo, Triangulum's black hole presents a puzzle of absence. Its stillness forces us to reconsider what we know about these cosmic titans, proving that sometimes the most profound mysteries aren't in the explosions or collisions, but in the silence between them. Now let's shift our gaze to a star so colossal, so luminous, it redefines the word giant. Nestled within the large Magellanic Cloud, a satellite galaxy orbiting our Milky Way, lies R136A1, a hypergiant that makes our Sun look like a flickering candle in comparison. This isn't just another big star, it's a cosmic behemoth that pushes the limits of what we thought possible. With a mass over 250 times that of the Sun and a brightness nearly 9 million times greater, R136A1 isn't just breaking records, it's shattering the rulebook of stellar physics. What makes this star so extraordinary isn't just its size, but the way it defies everything we know about how stars live and die. According to conventional models, stars this massive shouldn't even exist. The upper limit for stellar mass was long thought to be around 150 solar masses, based on the balance between radiation pressure and gravity. But R136A1 laughs in the face of those calculations. Its sheer intensity blasts out winds of plasma at speeds that could cross Earth's orbit in mere hours, and its surface burns at over 50,000 degrees Celsius, so hot it glows blue-white like a welder's torch. Yet the real mystery isn't just how it formed, but how it's surviving. Stars this massive are supposed to tear themselves apart, their own radiation so powerful it should blow away their outer layers in a matter of millennia. R136A1, though, has clung to its gargantuan mass far longer than expected, as if it's cheating the cosmic clock. Some astronomers speculate it might be the product of a rare stellar merger, two massive stars colliding and merging into one unstoppable force. Others wonder if it's feeding off surrounding material like a cosmic vampire, sustaining itself in ways we've never observed. Then there's the inevitable question, how will it end? Hypergiants like R136A1 don't fade quietly. When its time comes, it won't just go supernova, it might trigger a hypernova, an explosion so violent it could outshine entire galaxies for weeks. Even more chilling is the possibility of a pair instability supernova, where the star's core collapses so catastrophically that it leaves behind no black hole, no remnant, just pure, annihilating energy. But here's the twist. If that happens, it would scatter heavy elements across the cosmos in quantities that could seed future star systems with the building blocks of life. R136A1 isn't just a star, it's a cosmic rebel, challenging our understanding of stellar evolution at every turn. Its existence forces us to reconsider how stars are born, how they live, and how they die, proving that even in the local group, the universe still has secrets tucked away in the most dazzling corners. And as we watch it blaze defiantly against the void, one thing becomes clear. the rules of the cosmos are far more flexible than we ever imagined. Far from the blaze of hypergiants like R136A1, another cosmic anomaly hums with quiet defiance the small Magellanic Cloud's NGC 346. On the surface, this sprawling nebula looks like countless others, a luminous tapestry of gas and dust where stars are born, but peer closer and the numbers stop making sense. For a galaxy as petite as the small Magellanic Cloud, a dwarf satellite trailing our Milky Way NGC 346 is producing massive stars at a rate that would put sprawling galactic hubs to shame. It's as if a tiny village suddenly started birthing Olympic athletes every other day. The puzzle lies in the physics of starbirth. Normally, the larger a galaxy is, the more raw material it has to forge stars, especially heavyweight ones. Yet here, in this modest cosmic backwater, massive stars are emerging 10 times faster than predicted. Picture a matchbox that somehow spits out bonfires. How is this possible? Astronomers have a few leads. One clue comes from the nebula's pristine gas. Unlike in bigger galaxies, it's barely touched by heavy elements, resembling the primordial soup of the early universe. This simplicity might let gas collapse more easily into dense knots, igniting stars with freakish efficiency. But there's a twist. NGC 346 isn't just birthing stars, it's organizing them. Infrared observations reveal intricate tendrils of dust weaving through the nebula like cosmic rivers, channeling material into centralized hubs where stellar nurseries cluster. It's a level of coordination rarely seen in such small galaxies, almost as if some unseen hand is herding the chaos. Some theories suggest past collisions with other gas clouds could have triggered this frenzy, while others propose that the small Magellanic Cloud's low gravity lets stellar winds sculpt the gas into these perfect star-forging factories. Then there's the ultimate question: what happens when these stars die? A surge of massive stars means a future littered with supernova, neutron stars, and black holes, enough to rewrite the galaxy's structure. NGC 346 isn't just breaking rules, it's sketching a blueprint for how dwarf galaxies might seed the universe with new elements, one defiant star at a time. And as we watch this humble corner of space challenge every expectation, it's a reminder that sometimes the most revolutionary forces come in the smallest packages. Tucked away in the sprawling cosmic neighborhood of our local group lies a celestial oddity that shouldn't exist, the Fornax dwarf galaxy. At first glance, this modest collection of stars seems unremarkable, a faint smudge of light overshadowed by giants like Andromeda or the Milky Way. But look closer and something extraordinary emerges. Fornax, a galaxy barely 1% the mass of our own, is littered with globular clusters, dense, ancient balls of stars that usually belong to galaxies 10 times its size. It's like stumbling upon a tiny village with a skyline packed with skyscrapers, defying every architectural norm we know. Globular clusters are cosmic relics, often forming in the violent early universe when galaxies were just taking shape. Most galaxies hold onto a handful of them, with giants like the Milky Way boasting around 150. Fornax, though, has 6. That might not sound like much until you consider its scale. Imagine a small town with 6 massive stadiums. It's not just unusual, it's downright impossible by our current understanding of galactic economics. Where did these clusters come from? Why hasn't Fornax, with its feeble gravity, lost them to larger neighbors over billions of years? One theory suggests Fornax might be the survivor of a far grander past. Perhaps it was once a much larger galaxy, stripped of its stars by repeated collisions, leaving only its tightly bound globular clusters behind like stubborn debris after a storm. There's evidence to support this. Some of Fornax's clusters orbit in a vast, elongated stream, as if they were once part of a structure that's since been torn apart. Another possibility is even more intriguing. What if these clusters didn't form in Fornax at all? Simulations show they could have been stolen from smaller galaxies during ancient mergers, hoarded like cosmic treasure in Fornax's faint gravitational grip. But here's the twist: some of these clusters are too young. Globular clusters are supposed to be fossils, yet a few in Fornax show signs of relatively recent star formation, as if the galaxy somehow reignited their stellar furnaces long after the early universe's fireworks faded. This raises a tantalizing question. Could Fornax still be forging new clusters, defying the usual rules of galactic retirement? Or are we seeing the aftermath of some rare event, like a gas-rich collision that sparked a second wave of cluster birth? The implications ripple far beyond Fornax. If tiny galaxies can hold onto, or even create globular clusters so efficiently, it challenges our models of how galaxies evolve. Maybe these clusters are more resilient than we thought, clinging to their galactic hosts against all odds. Or perhaps Fornax is a cosmic outlier, a freak accident that forces us to reconsider the diversity of galactic life. Either way, its overabundance of clusters isn't just a curiosity. It's a clue whispering secrets about the chaotic, messy processes that shape even the smallest corners of the universe. And as we unravel its mysteries, one thing becomes clear: when it comes to galaxies, size isn't everything. Sometimes the most profound lessons come from the most unexpected places. The Sculptor dwarf galaxy might look like just another faint smudge in the night sky, but beneath its unassuming glow lies a cosmic heavyweight of the most mysterious kind. This tiny galaxy, barely 1/10,000th the mass of the Milky Way, is almost entirely made of dark matter, a ghostly presence so dominant it flips our understanding of galactic structure on its head. Imagine a city where 99% of the population is invisible, their presence only revealed by the way streetlights sway when no one's there. That's Sculptor's paradox, a galaxy where the stars are mere ornaments, floating atop an ocean of something we can't see. What makes Sculptor so puzzling isn't just the amount of dark matter it holds, it's how that matter is arranged. In most galaxies, dark matter forms a diffuse halo, gently cradling the visible stars and gas. But here, the dark matter is so densely packed, it's as if someone crammed an entire galaxy's worth into a space far too small. The stars, by comparison, seem like an afterthought, scattered thinly across an invisible scaffold. This extreme imbalance defies the typical recipe for galaxy formation, where visible matter and dark matter grow together in harmony. Sculptor, though, looks like a cosmic oversight, a place where the dark matter forgot to invite the stars to the party. One leading theory suggests Sculptor might be a failed galaxy, a relic from the early universe that never quite got its act together. Billions of years ago, it could have been on track to grow into something grander, but its sparse gas reserves starved it of the material needed to birth more stars. Over time, supernova or galactic tides might have stripped away what little visible matter it had, leaving behind a dark matter skeleton. Alternatively, it could be a survivor of multiple collisions, its stars ripped away by larger neighbors while its resilient dark matter core held firm. But here's where things get even stranger. Sculptor's dark matter doesn't behave like we'd expect. Observations show its stars move in ways that suggest the dark matter isn't clumping at the center, as most models predict. Instead, it spread surprisingly smooth, like butter evenly smeared across toast, a distribution that's left theorists scratching their heads. Some speculate this could hint at dark matter particles interacting with each other in ways we haven't accounted for, or even that our theories about gravity itself need revising. The implications ripple far beyond this one faint galaxy. If places like Sculptor are more common than we thought, they could rewrite the cosmic ledger, forcing us to reconsider how galaxies assemble and evolve. They might even hold the key to unlocking dark matter's true nature after all. Studying a galaxy that's mostly dark matter is like having a neutrino detector made entirely of neutrinos. It's a rare, unfiltered glimpse into the invisible architecture of the universe, and so the Sculptor dwarf galaxy stands as a silent challenge to our cosmic hubris. Its eerie dominance of dark matter reminds us that what we see in the night sky is just the glittering surface of a far deeper mystery, one that's waiting patiently for us to unravel. The Leo I dwarf galaxy should be forgettable, a faint, unassuming speck hovering near the Milky Way's halo, one of dozens of such satellites drifting in our gravitational shadow. But this tiny galaxy has a secret. It spins, and not just a lazy, predictable rotation, but a sharp, coordinated motion that defies everything we know about dwarf galaxies. Most of these small cosmic companions are chaotic blobs, their stars meandering in random orbits like bees around a hive. Leo I, though, moves with eerie precision, its stars sweeping around a common axis as if guided by an unseen hand. Here's what makes this so bizarre. Dwarf galaxies aren't supposed to rotate like this. Their gravity is too weak to orchestrate such orderly motion, and their turbulent histories plagued by collisions and tidal stripping should have scrambled any coherent spin long ago. Yet Leo I stars whirl in near-perfect sync, a ballet unfolding in slow motion across millions of years. It's as if someone took a grand spiral galaxy and shrank it down to 1% of its size, keeping the rotation intact. One possibility is that Leo I isn't as fragile as it seems. Hidden reservoirs of dark matter could be anchoring its spin, acting as an invisible scaffold that prevents its stars from flying apart. Measurements suggest this galaxy might be up to 90% dark matter, a staggering ratio even for dwarfs, but that raises another puzzle. Why hasn't the Milky Way's gravity torn this delicate rotation apart? Our galaxy's tidal forces should have warped or erased such precise motion over billions of years. Unless, of course, Leo I is a recent arrival, a cosmic interloper that's only now falling into the Milky Way's grasp. Then there's the rogue theory. What if Leo I's spin isn't natural at all? Some researchers have floated the idea that it could be the remnant of a much larger galaxy, its outer stars ripped away by ancient collisions, leaving only this stubbornly spinning core behind. Others speculate that its rotation might be the aftermath of a close encounter with another dwarf, a gravitational kick that set its stars whirling like a top. But the most tantalizing clue lies in Leo I's odd chemical makeup. Its stars are surprisingly rich in heavy elements for a dwarf galaxy, hinting at a violent past where supernova explosions might have injected energy and angular momentum into its gas. Could this have jump-started its rotation like a spoon stirring cream into coffee? If so, it'd mean dwarf galaxies are far more dynamic than we thought, capable of transforming themselves through their own stellar fireworks. Leo I's defiance is a reminder that even the smallest galaxies hold surprises. Its stubborn spin challenges our assumptions about how such systems form and evolve, proving that the universe never follows the script we write for it. And as we peer deeper into its mysteries, one thing becomes clear. In the cosmic dance of gravity and motion, even the faintest players can lead us to the most profound revelations. The Leo II dwarf galaxy might seem like just another quiet neighbor orbiting the Milky Way until you notice the cosmic breadcrumbs it's leaving behind. Stretching far beyond its faint stellar body, a delicate ribbon of stars winds through space like a celestial wake, telling a story of ancient violence. This stellar stream, over 30,000 light-years long, is no ordinary feature. It's the smoking gun of a galactic collision, evidence that Leo II didn't always drift alone in the darkness. Most dwarf galaxies are simple affairs, puffy clouds of old stars with little structure. But Leo II's stream suggests a dramatic past. Imagine throwing a stone into a pond, then watching the ripples freeze mid-motion. That's what astronomers see here. The stars in this trail move in perfect unison, all fleeing the dwarf galaxy's core at the same angle and speed. This isn't random scattering, it's the signature of a gravitational trauma, most likely a close encounter with another galaxy billions of years ago. The physics is unmistakable, like watching dust spiral behind a car on a dirt road. The stream marks the path of Leo 2's ancient assailant, but here's where the mystery deepens. Based on the stream's shape and the star's motions, whatever plowed through Leo 2 must have been massive, perhaps even another dwarf galaxy 3 or 4 times its size. Yet no obvious culprit remains nearby. Did the intruder galaxy merge with the Milky Way long ago, leaving only this stellar scar as evidence? Or could Leo 2 itself be the survivor of that collision, its former attacker now torn apart and lost to time? The stream's chemistry adds another layer of intrigue. Unlike the mostly metal-poor stars in Leo 2's core, the stream contains pockets of surprisingly youthful stars rich in heavier elements. This suggests the disrupting event might have triggered brief, violent bursts of new star formation like cosmic aftershocks rippling through the galaxy's gas. Some models even propose that the collision compressed gas clouds so intensely that they ignited stars millions of years after the initial impact, leaving these unusual chemical fingerprints. What makes Leo 2's stream so valuable isn't just the story it tells about this one small galaxy. It's what it reveals about the hidden turbulence of galactic neighborhoods. For every serene dwarf we see today, there might have been a dozen chaotic mergers in the past, shaping the cosmos in ways we're only beginning to decipher. This ghostly trail of stars is more than debris. It's a time capsule, preserving the echoes of a violent encounter that might have otherwise faded into oblivion. And as we trace its path across the sky, we're reminded that even the quietest corners of space can hold the loudest secrets. The Ursa Minor dwarf galaxy should be just another quiet satellite orbiting the Milky Way, a faint smudge of old stars held together by the invisible grip of dark matter. But this unassuming galaxy has become the center of a cosmic controversy that's shaking the foundations of astrophysics. Some studies suggest it might be missing something fundamental, its dark matter. If true, this would upend one of cosmology's core principles. That dark matter is the hidden scaffolding of all galaxies, big or small. Imagine building a house without a frame, relying only on the wallpaper to hold up the roof. That's how baffling Ursa Minor's case is. Dark matter is supposed to outweigh visible matter 5 to 1, its gravity preventing galaxies from flying apart. Yet when astronomers measured the motions of Ursa Minor's stars, they found something startling. The stars move slower than expected, as if the galaxy's gravity is far weaker than it should be. In a normal dwarf galaxy, dark matter's pull would keep stars whirling at higher speeds, like a spinning ice skater with arms tucked in. But Ursa Minor's stars drift lazily, like the skater's arms are outstretched, hinting there might be no invisible anchor at all. The implications are staggering. If Ursa Minor truly lacks dark matter, it challenges the very idea that galaxies can't form without it. One theory suggests the galaxy might have been stripped of its dark matter long ago, perhaps during a close encounter with the Milky Way. Just as tides pull water from the ocean, our galaxy's gravity could have wrenched away Ursa Minor's dark halo, leaving only the visible stars behind. But there's a problem with this idea. Simulations show such stripping should shred the galaxy entirely, dispersing its stars into a shapeless cloud. Ursa Minor, though, still holds a coherent structure, just one that moves like it's running on empty. Then there's the other possibility. Maybe we're reading the data wrong. Some researchers argue that Ursa Minor's stars aren't actually moving as slowly as they appear. The galaxy could be elongated along our line of sight, tricking us into underestimating its true velocity. Others propose that its dark matter isn't missing, just distributed in an unexpected way, like a diffuse fog rather than a concentrated core. This would make its gravitational footprint harder to detect, though no less real. But the boldest explanation is the most unsettling. What if dark matter isn't the universal glue we thought? A handful of galaxies, including the famous NGC 1052DF, also show signs of being dark matter deficient. Could these outliers be evidence of a flaw in our models? Or do they point to something even weirder like dark matter interacting with itself in ways we've never predicted? The controversy isn't just academic. If galaxies can exist without dark matter, it forces us to rethink how the universe assembles itself. Dark matter isn't just an add-on to our theories, it's the foundation. Without it, the entire cosmic web, the vast, invisible structure that binds galaxies together, might need reimagining. And that's what makes Ursa Minor's mystery so electrifying. It's not just a puzzle about one small galaxy. It's a test of whether we've misunderstood the rules of the universe itself. As astronomers debate, Ursa Minor looms quietly in the night sky, its stars drifting in defiance of expectation. Whether it's a cosmic anomaly or a sign of deeper truths waiting to be uncovered, one thing is certain. This faint smudge of light is forcing us to question everything we thought we knew about the hidden machinery of the cosmos. The Draco dwarf galaxy might be one of the faintest members of our local group, but it holds a distinction that puts it in a league of its own. Its stars are ancient. Not just old, but pristine, relics from the universe's infancy that have remained virtually unchanged for over 13 billion years. While most galaxies, even small ones, show signs of occasional stellar rebirth, pockets of gas collapsing into new stars, Draco has been stuck in a cosmic time capsule. Its star-forming factories shut down so completely it's like the galaxy fell asleep and never woke up. What makes Draco's stillness so striking is how unusual it is. Dwarf galaxies are typically messy, chaotic places where star formation flickers on and off like a faulty light bulb. Gas clouds collapse, supernova explode, and the cycle repeats. But Draco's stars tell a different story. Spectroscopic studies reveal almost no heavy elements, the telltale debris of stellar explosions that seed future generations of stars. Instead, its stars are made of nearly pure hydrogen and helium, the raw materials of the early universe. It's as if Draco skipped the cosmic recycling program entirely, preserving its first and only batch of stars like a museum exhibit frozen in time. Why did star formation here grind to a halt so abruptly? One clue lies in Draco's environment. Orbiting the Milky Way at a distance of about 250,000 light-years, it spent eons drifting through the sparse outskirts of our galactic halo, far from the dense gas clouds that might have reignited its stellar engines. But isolation alone can't explain its extreme quiet. Other remote dwarfs show at least sporadic star birth. Draco, though, seems to have been drained of its gas entirely, and not by its own stars. Its lack of heavy elements suggests it never had enough supernova to blow away its fuel. The leading theory is darker. The Milky Way's gravitational tides might have stripped Draco's gas away eons ago. As the dwarf galaxy swung close on an ancient orbit, our galaxy's pull could have siphoned off its star-forming material like a cosmic thief, leaving only its oldest stars behind. Computer simulations support this idea, showcasing how even gentle, repeated tugs from a massive neighbor can leave a small galaxy gas-starved and sterile. Yet there's a twist. Some of Draco's stars orbit in a peculiar disk-like arrangement, hinting that it might have resisted total disruption, clinging to some semblance of structure despite the robbery. Alternatively, Draco could have been born unlucky. If it formed in a region of the early universe unusually devoid of gas, it might never have had the chance to create more than its initial stellar population. This would make it a rare fossil of the primordial cosmos, a place where the conditions were so austere that star formation was doomed from the start. But the most tantalizing possibility is that Draco's ancient stars are hiding clues about dark matter. Dwarf galaxies are thought to be dominated by this mysterious substance, and the way their stars move can reveal its distribution. In Draco, the star's motions suggest its dark matter halo is incredibly dense and compact, unlike the fluffier halos of more active dwarfs. Could this unusual dark matter configuration have smothered star formation somehow? Some models propose that dense dark matter halos might prevent gas from cooling and collapsing, effectively strangling a galaxy's ability to birth new stars. If true, Draco isn't just a relic, it's a cosmic experiment showing us how dark matter's grip can shape a galaxy's destiny. The silence of Draco's stellar nursery is more than a curiosity, it's a window into the universe's earliest epochs. Its stars, untainted by the pollution of later generations, are like celestial archaeologists, preserving the chemical signature of a time before most galaxies even existed. And as we study this quiet, unassuming dwarf, we're reminded that sometimes the most profound secrets aren't shouted across the cosmos, but whispered by the light of stars that have burned since the dawn of time. The Sextans dwarf galaxy isn't just another faint satellite orbiting the Milky Way, it's a cosmic time machine. Nestled within its dim glow are stars so chemically primitive, they're like fossils from the universe's infancy. While most galaxies, even small ones, show signs of stellar generations building atop one another, each wave of stars enriching the next with heavier elements, Sextans breaks the mold. Its stars are staggeringly metal-poor, some containing less than 1/10,000th the iron of our Sun. For astronomers, this isn't just a curiosity, it's a direct line to understanding how the first stars in the cosmos lived and died. What makes Sextan stars so extraordinary isn't just their lack of metals, it's the sheer number of them. In most galaxies, metal-poor stars are rare treasures, often overshadowed by younger, richer generations. But here, they dominate the population, as if the galaxy skipped the cosmic cycle of rebirth entirely. Imagine finding an isolated village where every resident is over 100 years old, with no children or grandchildren in sight. That's the enigma of Sextans, a place where time seems frozen moments after the Big Bang. The leading theory is as fascinating as it is simple. Sextans might be a relic of the universe's first galactic building blocks, a living fossil that avoided the collisions and mergers that typically trigger star formation in larger galaxies. Without these violent interactions, its gas reservoirs remained untapped, leaving its primordial stellar population untouched. There's evidence to back this up. The galaxy's stars orbit in a disordered, puffy sphere, unlike the neat disks of more active dwarfs. This chaos suggests Sextans never experienced the gravitational shuffling that comes with galactic growth, preserving its ancient state like amber trapping an insect. But there's a twist. Some of Sextan's stars aren't just metal-poor, they're ultra-metal poor, with compositions so pristine they rival the most primitive stars ever found. These outliers challenge our understanding of how early star formation worked. Current models suggest the first stars were monstrously massive, burning out quickly in supernova that peppered the cosmos with heavier elements. Yet Sextan's ultra-metal poor stars don't fit neatly into this picture. Their chemistry hints at a more nuanced origin, possibly forming from the diluted debris of those first supernova, or even from pockets of unpolluted gas that survived longer than expected. Then comes the million-dollar question: why did Sextans stop making stars so abruptly? Unlike other dwarfs that flicker on and off, Sextans appears to have shut down completely after its initial burst. One clue lies in its environment. Situated over 280,000 light-years from the Milky Way, it's far enough to avoid tidal disruption but close enough to feel our galaxy's gravitational influence. Some researchers propose that the Milky Way's halo may have stripped away Sextan's remaining gas over billions of years, starving it of the fuel needed for new stars. Others speculate that its own supernova, those few that occurred, might have blown out its gas in a single, dramatic exhalation. The implications reach far beyond this one quiet galaxy. Sextans offers a rare, undisturbed sample of the early universe's chemical makeup. Its stars act as cosmic archaeologists, preserving the composition of the primordial gas from which they formed. By studying them, we can peer back to an era before galaxies had fully taken shape, testing theories about how the first stars seeded the cosmos with the building blocks of planets and life. But the biggest revelation might be what Sextans doesn't have. Unlike other ancient dwarfs, it shows no signs of dark matter-driven star formation, challenging the idea that dark matter is solely responsible for igniting the universe's first stellar fires. Its existence suggests alternative pathways for galaxy formation, ones that don't rely on the dense dark matter clumps we've long assumed were essential. In the grand tapestry of the local group, Sextans is a single thread, but one woven from the universe's earliest fibers. Its silent, metal-poor stars are more than just relics. They're messengers from a time when the cosmos was raw, untamed, and utterly unlike anything we see today. And as we decode their secrets, we're not just learning about a single dwarf galaxy, we're uncovering the origin story of everything. The Carina dwarf galaxy is a cosmic contradiction, a tiny, unassuming speck of stars that somehow packs more drama into its history than galaxies 10 times its size. While most dwarf galaxies form stars at a slow, steady trickle, Carina's story reads like a series of explosive chapters, each separated by eons of eerie silence. Its stars aren't just old or young. They're clustered into distinct age groups like generations frozen in time, revealing a rhythm of birth and dormancy that defies everything we thought we knew about how small galaxies evolve. The first clue to Carina's erratic past lies in its color magnitude diagram, a tool astronomers use to decode stellar populations. Instead of a smooth gradient of stars, the data shows sharp peaks, like the heartbeat of a patient waking from coma after coma. 3 distinct bursts of star formation stand out, one around 13 billion years ago, another 7 billion years back, and a final flare-up just 2 billion years in the past. Between these bursts, nothing. No star formation, no gas clouds collapsing, just cosmic radio silence. It's as if Carina turned its stellar factories on and off at will, ignoring the rules that govern every other galaxy in the local group. What could cause such extreme starts and stops? The answer might lie in Carina's turbulent relationship with the Milky Way. Dwarf galaxies orbiting larger hosts often experience tidal shocks, gravitational jolts that compress their gas and ignite star formation. But Carina's bursts are too sharp, too cleanly separated to be random. Some theorists propose it's caught in a resonant orbit, swinging close to the Milky Way at precise intervals that trigger these fireworks. Each time it dives through the densest part of our galaxy's dark matter halo, the pressure might squeeze its gas just enough to spark a new wave of stars before the galaxy retreats, exhausted into the cosmic dark. But there's another twist: Carina's gas reservoir. Unlike most star-forming dwarfs, it hasn't been completely stripped away by the Milky Way's gravity. Instead, it's been partially preserved, like a bank account that's periodically drained and then mysteriously refilled. This suggests Carina might have cannibalized smaller companions during its travels, stealing their gas to fuel its sporadic bursts. Alternatively, its own supernova could have blown gas outward in violent waves, only for it to cool and fall back in later epochs, like a cosmic fountain recycling its own debris. The most tantalizing possibility, though, involves dark matter. Computer simulations show that dense clumps of dark matter within Carina could act like gravitational lenses, focusing and amplifying the effects of tidal forces in unpredictable ways. If these clumps are arranged just right, they might create pockets of extreme pressure at irregular intervals, explaining the galaxy's bizarre on-off star formation. It's a reminder that even the smallest galaxies are puppeteered by forces we're only beginning to understand. Carina's stuttering history isn't just a curiosity, it's a challenge to the conventional narrative of galactic evolution. Most models assume dwarfs form stars continuously until their gas runs out. But Carina proves the universe is messier, more inventive than our textbooks. Its episodic bursts suggest that star formation isn't always a smooth decline from youth to old age. Sometimes it's a series of second acts, each one rewriting the galaxy's destiny. And as we piece together the clues hidden in its stellar generations, we're forced to confront a humbling truth. When it comes to galaxies, there's no such thing as a simple life story. The Antlia II galaxy shouldn't exist, at least not the way we see it. This cosmic specter, drifting silently through the local group, is so faint, so ghostly, that astronomers almost missed it entirely. Discovered only in 2018, Antlia II isn't just dim. It's one of the most diffuse galaxies ever found, its stars scattered so thinly that its glow is 5,000 times weaker than the Milky Way's. If you held a handful of glitter and tossed it into a swimming pool, the sparse, flickering light would still be denser than this galaxy. Yet against all odds, it's here, a wispy, sprawling enigma orbiting our own galaxy like a shadow you can barely see. What makes Antlia II truly bizarre isn't just its faintness, but its sheer size. Spanning nearly 20,000 light-years, it's as wide as the Milky Way's disk but contains less than 1/1,000,000th the stars. Picture a city the size of New York with only a dozen streetlights. That's the staggering emptiness of this galaxy. Normally, a structure this large should have collapsed under its own gravity, condensing into something tighter and brighter. The fact that it hasn't suggests something unseen is holding it together. That invisible scaffolding, likely dark matter, but in a configuration so unusual, it's rewriting the rules of galactic survival. The leading theory is that Antlia II is a puffed-up dwarf, its stars stretched thin by violent encounters with the Milky Way. Simulations show our galaxy's gravity might have ripped through Antlia II multiple times over billions of years, stripping away its gas and scattering its stars like leaves in a hurricane. But here's the puzzle. Even after such abuse, most dwarfs end up compact, their stars pulled into a dense core. Antlia II did the opposite. It expanded, as if some hidden force was pushing its stars outward. Some researchers speculate its dark matter halo might be uniquely fluffy, acting less like a magnet and more like a cushion, resisting compression in ways we've never seen. Then there's the dark horse explanation. Antlia II might not be a traditional galaxy at all. Its stars move peculiarly, with motions so sluggish they barely seem bound by gravity. This has led a few bold theorists to suggest it could be the remnant of a failed galaxy, a place where dark matter never clumped densely enough to ignite robust star formation, leaving behind only this skeletal husk. Alternatively, it might be the debris of a long-vanished galaxy, its stars lingering like smoke after a fire, their original structure long since erased. The implications ripple far beyond this one ghostly galaxy. If Antlia II's extreme diffuseness is due to unique dark matter properties, it could hint at entirely new behaviors for this mysterious substance. Perhaps dark matter interacts with itself in ways we haven't accounted for, or maybe it can exist in low-density states that defy our simulations. Either way, Antlia II is a cosmic challenge, a whisper from the shadows, reminding us that even in our own backyard, the universe still has secrets we've only begun to glimpse. And so, Antlia II drifts on, barely there yet impossible to ignore. Its very existence forces us to question what a galaxy really is, how tenuous the boundaries between presence and absence can be. In the grand tapestry of the local group, it's a thread so fine it nearly vanishes, yet pull on it, and the whole picture might just unravel. The Crater II dwarf galaxy doesn't follow the rules. On paper, it's massive, stretching nearly 7,000 light-years across, making it one of the largest dwarf galaxies orbiting the Milky Way. But here's the catch. It's so dim, so ghostly faint, that if you blinked while looking at it through a telescope, you'd miss it entirely. This paradox, a galaxy with the size of a Titan and the glow of a candle, has astronomers scratching their heads, forcing them to reconsider what it even means to be a galaxy in the first place. What makes Crater II so baffling is its sheer emptiness. Despite its sprawling dimensions, it contains fewer stars than some globular clusters, objects hundreds of times smaller. Imagine an empty football stadium with only 3 spectators. That's the kind of haunting vacancy we're dealing with. Normally, a structure this large should have collapsed under its own gravity, compressing into something denser. The fact that it hasn't suggests something invisible, likely dark matter, is holding it together in an unusually fluffy configuration, but even that explanation doesn't quite fit. Here's the problem. Crater 2's dark matter halo, if it exists, doesn't behave like the halos we see in other galaxies. Its stars move sluggishly, as if the galaxy's gravity is far weaker than its size implies. One leading theory is that Crater 2 might be the aftermath of a cosmic near-miss, a close encounter with the Milky Way that stretched it like taffy, pulling its stars apart while leaving its dark matter intact. Computer simulations show our galaxy's tidal forces could have done this, but there's a twist. Crater 2's orbit doesn't quite match the expected path of a galaxy that's been violently disrupted. Another possibility is even stranger. Crater 2 might be what's left of a failed giant, a galaxy that formed in the early universe with an unusually sparse dark matter core, preventing it from ever gathering enough gas to ignite robust star formation. Without that dense gravitational anchor, its stars would have remained scattered like seeds thrown onto thin soil. This would make Crater 2 a cosmic oddity, a galaxy born too diffused to ever thrive, a shadow of what it could have been. But the most tantalizing clue lies in Crater 2's surroundings. Recent observations reveal a faint stream of stars trailing behind it, like breadcrumbs marking its path through space. This suggests the galaxy might not be alone. It could be the brightest remnant of a group of ultra-diffuse galaxies, all torn apart by the Milky Way's gravity over billions of years. If true, Crater 2 isn't just a fluke, it's a survivor, the last visible piece of a once larger structure now lost to time. The implications ripple beyond this one ghostly galaxy. Crater 2's existence challenges our definition of what makes a galaxy a galaxy. Is it the number of stars, the density, the presence of dark matter, or something else entirely? By studying this cosmic contradiction, we're forced to confront how much we still don't understand about the invisible framework shaping the universe, and how even the faintest whispers in the night sky can upend everything we thought we knew. The Tucana dwarf galaxy is a hermit in the cosmic wilderness, a lonely island of stars adrift in the emptiness between galactic giants. While most galaxies in the local group huddle near the Milky Way or Andromeda, Tucana keeps its distance, floating over 2 million light-years away in the celestial no-man's land near the southern constellation it's named after. This isolation isn't just a curiosity, it's a time capsule. Unlike galaxies that constantly collide, merge, and borrow stars from their neighbors, Tucana has been left alone for billions of years, preserving a stellar population so ancient, it's like stepping into the universe's toddler years. What makes Tucana extraordinary isn't just its age, but its pristine condition. Its stars are metal poor to an extreme, containing barely a trace of elements heavier than hydrogen and helium. The telltale signs of a galaxy that stopped forming stars when the universe was still in its infancy. Think of it as a cosmic fossil, untouched by the pollution of later supernova or the gravitational meddling of passing galaxies. While other dwarfs show scars from violent encounters, Tucana's stars move in relaxed, disordered orbits like a crowd that's never been pushed or squeezed. This undisturbed state gives astronomers something rare, a pure sample of the early universe's stellar recipe. But here's the puzzle: how did Tucana avoid the cosmic party? Most galaxies, even small ones, get pulled into the gravitational dance of larger neighbors eventually. The Milky Way's hungry halo has consumed dozens of dwarfs over its lifetime, and Andromeda's appetite is just as voracious. Yet Tucana remains defiantly solitary. Some theories suggest it might be moving too fast to be captured, like a comet whizzing past the sun without getting trapped. Others propose it's always orbited at the very edge of the local group's gravitational influence, where the pull of neighboring galaxies is too weak to drag it in. There's another possibility, one that's even more intriguing. Tucana might not belong to the local group at all. Its motion through space hints that it could be a recent visitor, a cosmic drifter that wandered into our neighborhood from the vast intergalactic void beyond. If true, it would explain why its stars are so untouched. They've spent most of cosmic history in true isolation, far from the chaotic crowdedness where galaxies typically evolve. This would make Tucana not just an outlier, but an ambassador from the emptiest regions of the universe, offering a glimpse of what galaxies look like when they grow up alone. Yet Tucana's solitude raises another mystery. Why did its star formation shut down so completely? Most isolated dwarfs flicker on and off, occasionally reigniting their stellar engines when gas drifts too close. Tucana, though, seems to have exhausted its fuel supply in one initial burst, then gone silent forever. One clue lies in its dark matter halo, or rather, its apparent lack of one. Measurements suggest Tucana's gravity is weaker than expected for its size, meaning it might have too little dark matter to hold onto gas over time. Without this invisible scaffolding, even a slight nudge from stellar winds or supernova could have blown its gas away permanently, leaving behind only these ancient stars as a memorial to its brief, fiery youth. The implications stretch far beyond this one quiet galaxy. Tucana's untouched stars are like pages from a cosmic diary, recording conditions in the universe's first 2 billion years with startling clarity. By studying their composition, we can test theories about how the earliest galaxies formed, and why some, like Tucana, became hermits while others grew into bustling metropolises like the Milky Way. Its existence forces us to confront how little we truly understand about the fringes of galactic society, where the rules of engagement seem to rewrite themselves in the silence between collisions. And so, the Tucana dwarf galaxy lingers on the edge of our awareness, a relic from a time before galactic empires rose. Its isolation isn't just a quirk of location, it's a statement. In a universe that thrives on interaction, Tucana stands as proof that some stories unfold best in solitude, and that the deepest cosmic secrets might be hiding in the quietest corners of the sky. The Pegasus dwarf irregular galaxy is cosmic chaos incarnate, a scrambled, lopsided tangle of stars and gas that looks less like a galaxy and more like the aftermath of a celestial car crash. Unlike the graceful spirals or neat ellipticals we're used to, Pegasus is a mess of disjointed clumps and jagged tendrils, its stars scattered as if tossed by a giant hand. There's no center, no symmetry, no order, just pure, unfiltered galactic anarchy, and that's exactly what makes it so fascinating. This isn't just a case of bad cosmic manners. Pegasus's disarray is a window into the violent processes that shape small galaxies. Most irregular dwarfs are turbulent, but Pegasus takes it to extremes. Its gas clouds billow outward in ragged filaments, lit by the erratic glow of newborn stars that erupt in sporadic bursts like fireworks set off at random. There's no rhythm to its star formation, no predictable cycles, just frenzied starbirth wherever the galaxy's internal turbulence churns gas into knots dense enough to ignite. It's as if the galaxy is constantly tripping over its own feet, stumbling from one stellar explosion to the next. What's causing this pandemonium? The prime suspect is gravity, or rather, the lack of it. Unlike larger galaxies, where gravity's firm grip organizes stars into orderly structures, Pegasus is too small to enforce cosmic discipline. Without a dominant central mass to steady it, every passing gas cloud or minor collision sends ripples of chaos through its fragile framework. Some astronomers compare it to a Jenga tower in a windstorm. Every nudge threatens to send another piece tumbling. But there's another twist: Pegasus might be a cannibal. Its ragged edges and multiple stellar clumps suggest it could be swallowing even smaller galaxies or gas clouds, each merger adding fuel to the bedlam. Imagine throwing a handful of glitter into a fan. That's the kind of messy aftermath we're seeing here. These chaotic meals could explain why parts of Pegasus glow with unusually young blue stars, while other regions seem frozen in time, their stars aging undisturbed for billions of years. The real revelation, though, is what Pegasus tells us about the early universe. Galaxies like this are thought to be relics of a time before gravity imposed cosmic law and order. In the universe's first few billion years, when galaxies were smaller and space was more crowded, such free-for-all structures may have been the norm. Pegasus, then, isn't just an oddball, it's a living fossil, a glimpse into the unruly adolescence of galactic evolution. Yet for all its chaos, there's a method to the madness. Close studies reveal faint patterns in the way Pegasus's stars move, subtle hints that dark matter might be weaving an invisible net beneath the pandemonium. Even in disorder, the universe finds a way to leave its signature, and that's the ultimate lesson of Pegasus. Sometimes the most revealing truths aren't found in the elegant spirals or perfect spheres, but in the glorious, untamed messiness of cosmic outliers. The Wolf-Lundmark-Melot galaxy is a relic hiding in plain sight, a time capsule of hydrogen so pristine. It's like stumbling upon a cave untouched for millennia, its walls still glistening with ancient moisture. While most galaxies have cooked their original gas into heavier elements over billions of years of star formation, WLM has held onto its primordial fuel with an almost defiant purity. Its hydrogen reservoirs remain nearly unchanged since the early universe, offering astronomers a rare chance to study the raw ingredients of cosmic creation before gravity, fusion, and supernova scrambled the recipe. What makes WLM's gas so extraordinary isn't just its age, but its isolation. Floating at the edge of the Local Group, over 3 million light-years from the Milky Way, this dwarf galaxy has avoided the gravitational bullies that typically strip smaller galaxies of their gas. Unlike satellites orbiting larger hosts, WLM's hydrogen hasn't been torn away by tidal forces or blown out by the relentless winds of supernova. Instead, it lingers in a state of quiet preservation, like an undisturbed pond reflecting the same sky for eons. But here's the catch: WLM isn't entirely dormant. Nestled within its ancient gas are pockets of newborn stars, proof that even the most primordial environments can still spark new life. These stars, though, are different. Born from nearly pure hydrogen and helium, they lack the heavy elements that pepper younger stellar populations. It's as if the galaxy is trying to recreate the universe's first stars, offering a glimpse into how the earliest luminaries might have ignited. The real revelation lies in the gas itself. Spectroscopic studies reveal WLM's hydrogen is eerily similar to the intergalactic medium of the early cosmos: cool, diffuse, and largely unmixed with heavier elements. This makes it a living laboratory for testing theories about how gas collapsed into the first galaxies. Simulations suggest early star formation required pristine gas to condense into dense enough clouds to ignite. But until WLM, we'd never found a nearby example so untouched by time. Yet WLM's gas isn't just a fossil, it's a puzzle. Despite its purity, the hydrogen isn't uniformly distributed. Instead, it clumps and filaments in ways that defy simple models of galactic evolution. Some regions are eerily calm, while others churn with turbulence, as if the galaxy can't decide whether to sleep or erupt. This inconsistency hints at something deeper, the possibility that even in the most primitive environments, chaos and order wage an eternal tug of war, shaping galaxies in ways we're only beginning to decipher. The implications stretch far beyond this one quiet dwarf. WLM's gas is a benchmark, a baseline against which we can measure how cosmic recycling alters matter over time. By comparing it to gas in younger galaxies, astronomers can trace the life cycle of elements from the Big Bang to the present, a kind of cosmic genealogy written in hydrogen's faint radio whispers. And then there's the tantalizing question, why has WLM's gas survived so long? Luck might play a role, its remote location shielding it from disruption, but some theorists propose a darker explanation. WLM's dark matter halo, though faint, could be unusually effective at sheltering gas, cradling it in a gravitational cocoon that resists stripping. If true, this would mean dark matter's role in preserving galactic fuel is more nuanced than we thought, varying wildly from one galaxy to the next. WLM isn't just a window into the past, it's a mirror reflecting how much we still don't understand about the universe's most basic building blocks. Its ancient hydrogen isn't merely a curiosity, it's a testament to the fact that some corners of the cosmos, against all odds, refuse to move on, clinging to the echoes of a time when everything was just beginning. Most galaxies wear a shroud of dust, a gritty veil of cosmic debris that dims and distorts the light of their stars. But IC1613 throws that rulebook out the airlock. This dwarf galaxy is freakishly clean, its interstellar environment so pristine, astronomers can peer straight through it like a freshly washed window. While most galaxies force us to squint through smoky corridors of dust and gas, IC1613 offers a crystal-clear view of every star, cluster, and nebula within it, a transparency so rare, it's rewriting our understanding of how galaxies evolve. What makes this galaxy's cleanliness so startling isn't just the absence of dust, it's the why. Interstellar dust typically forms when aging stars shed heavy elements, scattering carbon and silicon particles like cosmic confetti. Over time, these particles clump together, creating the murky haze we see in galaxies like the Milky Way. But IC1613 never got the memo. Its stars, though plentiful, seem to have skipped this messy phase entirely, leaving the galaxy's corridors eerily dust-free. It's like finding a bustling city without a single scrap of litter, a phenomenon so unnatural it demands an explanation. One clue lies in the galaxy's chemistry. IC1613 is metal poor even by dwarf galaxy standards, its stars lacking the heavy elements needed to seed dust formation. This suggests it might have formed in a pocket of the early universe unusually devoid of these ingredients, like a gourmet kitchen missing half its spices. But here's the twist. Despite this scarcity, IC1613 has still managed to birth new stars at a steady clip, proving that galaxies don't need dusty nurseries to keep their stellar factories running. Then there's the wind factor. Some galaxies expel dust through powerful supernova explosions or stellar winds, effectively deep cleaning their interstellar environments. But IC1613's supernova are too infrequent to account for its spotless state. Instead, astronomers suspect its pristine condition might be the work of an unseen cosmic janitor, ultraviolet radiation from its youngest, hottest stars. Unlike the gentle warmth of our sun, these massive stars blast out torrents of UV light, powerful enough to vaporize dust particles before they can clump together. Think of it as a galactic UV sterilizer perpetually scrubbing the galaxy clean. The implications go beyond mere curiosity. IC1613's clarity gives astronomers an unobstructed view of stellar evolution, free from the usual distortions of dust. Its stars can be studied with unprecedented precision, offering benchmark data for models of how stars form and age. But the galaxy also presents a paradox. If dust is so rare here, how do its gas clouds collapse into stars at all? Conventional wisdom says dust helps gas cool and condense, acting as a catalyst for starbirth. Yet IC1613's gas seems to defy this rule, forming stars efficiently despite its minimalist toolkit. This raises a tantalizing possibility. Maybe our understanding of star formation is incomplete. Perhaps in environments this pure, gas can collapse through alternative mechanisms like turbulent flows or magnetic fields, bypassing the need for dust entirely. If true, IC1613 isn't just an outlier, it's a living laboratory showcasing a road less traveled in galactic evolution. And so, this unassuming dwarf galaxy challenges us to rethink the basics. Its crystalline vistas aren't just a marvel to observe, they're a reminder that the universe always keeps a few tricks up its sleeve, revealing them only in the most unexpected places. In a cosmos often clouded by dust and mystery, IC1613 stands apart, offering a rare glimpse of the stars as they truly are: no filters, no obstructions, just pure, unadulterated starlight. The Phoenix dwarf galaxy is a cosmic phoenix in every sense, rising from its own ashes in a stellar rebirth no one saw coming. For billions of years, this unassuming speck of light floated quietly at the edge of the local group, its star-forming fires long since extinguished, its gas reserves seemingly exhausted. Astronomers had catalogued it as just another fossil, a relic of the early universe destined to fade into obscurity. Then came the shock. New stars began flickering to life in its ragged outskirts, defying every expectation of how small, ancient galaxies behave. This unexpected resurgence isn't just odd, it's a flat-out violation of galactic retirement rules. Dwarf galaxies like Phoenix are supposed to follow a predictable life cycle. They burn through their gas in a frenzied burst of early star formation, then sputter out as supernova and stellar winds blow away the remaining fuel. By all accounts, Phoenix had reached this endpoint over 10 billion years ago. Yet somehow, against all odds, it found a way to reignite. The first clue came from Hubble observations revealing clusters of bright blue stars, cosmic newborns, nestled among the galaxy's ancient red stellar population. It was as if a retirement home had suddenly started hosting baby showers. So where did this second wind come from? The leading theory points to an invisible lifeline, cold gas streaming in from intergalactic space. While Phoenix's original gas reserves were indeed depleted, simulations suggest it might have drifted through a filament of the cosmic web, a thread of primordial hydrogen left over from the Big Bang. Like a ship catching a sudden gust of wind, the galaxy could have siphoned off enough of this pristine fuel to spark a new round of star formation. Supporting this idea, radio telescopes have detected faint wisps of hydrogen wrapping around Phoenix's edges, though not enough to explain the sheer scale of its resurgence. That's where the plot thickens. Phoenix's dark matter halo might be playing an unseen role. Unlike larger galaxies, where dark matter's gravity is balanced by swirling disks of gas and stars, dwarf galaxies are dominated by their dark halos. If Phoenix's halo is unusually lumpy, it could have created pockets of intense gravity, pulling in stray gas over eons until critical mass was reached. Picture a spiderweb collecting dewdrops, each tiny capture adding up until suddenly there's enough to drink. But there's a wild card: interactions with other galaxies. While Phoenix appears isolated now, it might not always have been. Some models suggest a near miss with another dwarf galaxy could have jolted its remaining gas, compressing it just enough to ignite new stars. The tidal forces wouldn't have needed to be strong, just a gentle nudge to disturb the equilibrium. This would make Phoenix's rebirth less about fresh fuel and more about stirring the embers of what little it had left. The implications are profound. If galaxies can awaken after billions of years of dormancy, it means our theories about their life cycles are incomplete. Phoenix challenges the assumption that star formation is a one-way street, proving that even the oldest, quietest galaxies might harbor untapped potential. It also raises tantalizing questions about the cosmic web's role as a gas delivery system. Could other, dead galaxies be secretly refueling as we speak? Most thrilling of all is what Phoenix tells us about the early universe. Its new stars are forming in near-pristine gas, mirroring conditions from the cosmos's first billion years. By studying them, we're getting a front-row seat to how the very first stellar nurseries might have operated. In that sense, Phoenix isn't just defying expectations, it's offering us a time machine, a chance to witness the birth of stars as they happened when the universe was young. And so, this tiny galaxy, once written off as a cosmic has-been, now stands as a testament to the universe's endless capacity for surprise. Its unexpected rebirth reminds us that in the grand tapestry of the cosmos, no story is ever truly over. Sometimes, the most extraordinary chapters are those we never saw coming. The NGC 6822 galaxy doesn't just defy expectations, it obliterated them. When astronomer Edward Emerson Barnard first trained his telescope on this faint smudge of light in 1884, he had no idea he was looking at a cosmic revolutionary. Back then, the prevailing belief was that the universe consisted solely of the Milky Way, with everything else nebulae, star clusters existing within its boundaries. NGC 6822, later nicknamed Barnard's Galaxy in his honor, would become one of the first cracks in that crumbling worldview, a silent rebel proving there was far more to the cosmos than anyone dared imagine. What made Barnard's discovery so groundbreaking wasn't just the galaxy itself, but its stubborn refusal to fit the mold. Unlike the elegant spirals or globular clusters familiar to astronomers of the time, NGC 6822 was irregular, a chaotic jumble of stars and gas with no clear center or symmetry. Its very shape screamed otherness, a quality that puzzled scientists for decades. The final nail in the coffin came when Edwin Hubble, decades later, measured its distance and confirmed it lay far beyond the Milky Way's borders. Suddenly, Barnard's oddball smudge wasn't just a curiosity. It was a landmark, irrefutable proof that galaxies existed as independent, island universes dotting the cosmos. But NGC 6822's defiance didn't stop there. Even among irregular galaxies, it stands out for its metallicity, or rather, the lack of it. Its stars are impoverished in heavy elements, a trait typical of galaxies much farther back in time. This suggests Barnard's galaxy has been moving to its own rhythm for billions of years, forming stars at a leisurely pace while avoiding the violent collisions that typically enrich galactic gas with heavier elements. It's like finding a remote village that never industrialized, its traditions preserved in pristine isolation. Yet the galaxy's most tantalizing secret lies in its sprawling hydrogen clouds. Radio observations reveal vast reservoirs of this primordial gas, untapped and shimmering with potential. Unlike most dwarf galaxies, which get stripped of their fuel by larger neighbors, NGC 6822 has held onto its hydrogen like a cosmic miser, hoarding it for some future stellar burst we've yet to witness. Some astronomers speculate this could make it a ticking time bomb, a quiet galaxy biding its time before erupting into a fireworks display of newborn stars. Barnard's galaxy isn't just a relic of astronomical history, it's a living challenge to our assumptions. Its very existence forced humanity to rethink our place in the universe, and its continued oddities remind us that even in our own local group, the cosmos still has the power to surprise. Every observation peels back another layer, revealing not just the story of one small galaxy, but the grand, unpredictable narrative of how galaxies and our understanding of them evolve. The Aquarius dwarf galaxy is caught in a gravitational tug of war, and the evidence is written across the sky in streams of stolen starlight. This small satellite of the Milky Way isn't just orbiting our galaxy, it's being unraveled by it, leaving behind sprawling tidal tails that stretch over 500,000 light-years through space. These shimmering ribbons of stars aren't just debris, they're a cosmic autopsy, revealing the invisible forces shaping galaxies in real time. What makes Aquarius's tidal tails so extraordinary is their sheer scale. Unlike the faint, scattered streams left by other dwarf galaxies, Aquarius's stellar trails are dense and structured, arcing across the sky like the wake of a ship plowing through invisible waters. Each star in these tails carries a forensic record of the Milky Way's gravitational influence, their exact positions and velocities mapping the precise moments they were torn free. It's as if the galaxy is leaving breadcrumbs not to find its way home, but to mark where home once was. The physics behind this stellar theft is brutal yet elegant. As Aquarius orbits the Milky Way, our galaxy's gravitational pull is stronger on the dwarf's near side than its far side, a difference called tidal force. Over billions of years, this imbalance has stretched Aquarius like taffy, peeling away stars from its outer edges first. The resulting tails aren't random. They trace the dwarf's orbit with mathematical precision, one marking the path it came from, the other pointing toward where it's headed. Computer simulations show these streams should eventually wrap around the Milky Way entirely, creating a faint stellar halo most astronomers believe is built from the remains of countless devoured dwarfs. But Aquarius's tails hold surprises. Spectroscopic analysis reveals unexpected clumps of stars moving in unison, suggesting the galaxy wasn't just passively disrupted, it put up a fight. Some clusters in the streams are far denser than tidal theory predicts, hinting that Aquarius might have housed unusually robust star clusters that resisted disintegration longer than expected. Others show chemical signatures distinct from the dwarf's core, implying they originated from deep within Aquarius's gravitational well before being violently ejected. These anomalies are forcing scientists to revisit how galaxies lose their stars, with new models proposing that dark matter substructures within the Milky Way could be acting like cosmic knives, slicing the dwarf apart in unpredictable ways. The most tantalizing clue, though, lies in what's missing. For all the stars Aquarius has lost, its core remains stubbornly intact, a compact nugget of stellar light that refuses to dissolve. This resilience suggests the dwarf's dark matter halo, its invisible gravitational anchor, might be far denser than predicted. If true, it could mean Aquarius is being stripped from the outside in, its dark matter shielding its heart from total destruction. Some researchers even speculate this process could explain why we still see so many dwarf galaxies orbiting the Milky Way instead of just tidal streams. Their dark matter cores might be nearly indestructible, ensuring at least a ghostly remnant survives. Aquarius's dismemberment isn't just a spectacle, it's a preview. The same forces tearing it apart will one day shred the large Magellanic Cloud, and in the distant future, even Andromeda and the Milky Way will stretch each other into stellar rivers during their collision. These tidal tails are more than destruction. They're transformation, the universe's way of recycling galaxies into something new. And as we trace their shimmering paths across the sky, we're witnessing a dance older than Earth itself, the endless gravitational waltz that shapes everything from the tiniest dwarf to the grandest spiral. The Sagittarius dwarf spheroidal galaxy is living on borrowed time, a cosmic meal slowly being devoured by the Milky Way in one of the most spectacular displays of gravitational destruction ever observed. Once a proud, independent galaxy, it's now unraveling into a glittering river of stars known as the Sagittarius Stream, a stellar trail stretching over 1 million light-years across the night sky. This isn't just a passive disintegration, it's a full-scale galactic demolition, revealing the brutal mechanics of how large galaxies grow by consuming their smaller neighbors. The violence of this process is written in the stream's very structure. As the Sagittarius dwarf orbits the Milky Way, our galaxy's immense gravity peels away stars layer by layer, like an onion being unspooled into space. These stripped stars don't just scatter randomly, they follow precise orbital paths, forming vast, looping ribbons that wrap around the Milky Way like celestial tinsel. The most startling detail, this isn't the first time it's happened. The stream isn't a single tail but multiple nested strands, evidence that Sagittarius has completed at least 3 full orbits around the Milky Way, losing more of itself with each pass. But the real revelation lies in the stream's chemistry. The stars being torn away aren't uniform. They vary wildly in age and composition, painting a vivid portrait of the dwarf's tumultuous history. Some are ancient, metal-poor relics from the galaxy's earliest epochs, while others are surprisingly young, suggesting Sagittarius clung to its star-forming gas far longer than expected. This mix implies the dwarf wasn't always the feeble satellite we see today. Billions of years ago, it might have been a robust, gas-rich galaxy capable of multiple generations of stars, only to have its fuel stripped away by the Milky Way's relentless tides. What makes this demolition so scientifically precious is its immediacy. Unlike the Aquarius dwarf's slow-motion unraveling or the shredded remains of long-dead galaxies in our halo, Sagittarius is being dismantled right before our eyes. Astronomers can track individual star clusters being pulled from its core, measure the precise speed of its disintegration, and even predict its final fate. Simulations suggest that within another billion years, nothing will remain of the original dwarf. Just a few scattered star clusters embedded in the Milky Way's halo, like fossils in cosmic sediment. Yet the most profound lesson from Sagittarius isn't about destruction, it's about construction. Every star added to the Milky Way's halo through this process changes our galaxy's chemical makeup, enriching it with the dwarf's unique elemental signatures. In a very real sense, the Milky Way is growing not just in size but in complexity, building itself from the remains of lesser galaxies. This isn't just cannibalism, it's galactic alchemy, transforming simple dwarfs into the raw materials of a larger, richer structure. And so, the Sagittarius stream serves as both a memorial and a blueprint. It's the ghost of a galaxy that was and a preview of what's to come, because the Milky Way isn't done feasting. Dozens more dwarfs still orbit in its gravitational grip, destined to follow the same path. Their stars, too, will one day join the grand stellar tapestry of our galaxy, their origins erased but their legacy written in the light of 1,000 future suns. The Canis Major dwarf galaxy shouldn't be this controversial. Discovered in 2003, this faint smudge of stars was initially heralded as the closest known galaxy to the Milky Way, a mere 25,000 light-years from our solar system, tucked embarrassingly close in our own cosmic backyard. But almost immediately, astronomers began questioning whether it was a galaxy at all or just a mangled piece of our own. At the heart of the debate lies an unusual structure called the Monoceros Ring, a sprawling arc of stars wrapping around the Milky Way's disk like a celestial serpent. Some researchers argue this ring is the shredded remnant of the Canis Major dwarf, a small galaxy torn apart by our Milky Way's gravity over billions of years. The evidence seems compelling. The stars in this stream share distinct chemical signatures and move in coordinated orbits, suggesting a common origin outside our galaxy. Infrared surveys even revealed a dense knot of stars near the constellation Canis Major, which could be the dwarf's surviving core, still clinging to existence amidst the tidal wreckage. But skeptics fire back with an equally convincing case. The Milky Way's disk isn't perfectly flat. It warps and ripples like a vinyl record left in the sun. Could the Monoceros Ring just be a distorted ripple in our own galactic plane, a gravitational echo from some ancient disturbance? Computer simulations show the Milky Way's disk can produce similar structures when nudged by passing dwarf galaxies or dark matter clumps. Even the alleged core of Canis Major might just be a chance overdensity of Milky Way stars, a random clump masquerading as a galactic corpse. The plot thickens when you examine the stars themselves. Proponents of Canis Major's existence point to their metallicity. These stars are far poorer in heavy elements than most Milky Way disk stars, resembling the populations of other dwarf galaxies. Yet critics counter that our galaxy's outer disk also hosts metal-poor stars, remnants from its early, chaotic formation. It's like finding a piece of driftwood on a beach. Is it debris from a distant shipwreck or just a weathered branch from a nearby tree? Then there's the timing problem. If Canis Major was indeed a galaxy, when did the Milky Way destroy it? Some models suggest the encounter happened as recently as 1 billion years ago, which would make the remnants unusually fresh compared to other shredded dwarfs. Yet there's no obvious spike in the Milky Way's star formation rate around that time, something we'd expect if a gas-rich dwarf had recently plunged into our galactic disk. The controversy isn't just academic. If Canis Major is real, it's rewriting the Milky Way's history, proving our galaxy is still digesting victims in the cosmic present. If it's an illusion, it's revealing how little we understand the dynamic chaos of our own galactic backyard. Either way, this debate is a reminder that even in an age of space telescopes and supercomputers, the universe keeps its secrets well, sometimes hiding them in plain sight right under our noses. At the heart of the Andromeda galaxy lies a cosmic riddle wrapped in starlight, not one brilliant core but two. This dazzling duality, known as the double nucleus, defies everything we expect from galactic centers. Most galaxies, including our Milky Way, host a single dense cluster of stars orbiting a supermassive black hole. Yet Andromeda's core splits into two distinct brightness peaks just 5 light-years apart, glowing like mismatched headlights in the cosmic dark. The question isn't just why this exists, it's how such a delicate dance can persist without collapsing into chaos. The leading theory reads like a galactic crime scene. Astronomers suspect Andromeda's twin peaks are the aftermath of an ancient collision, where a smaller galaxy plunged into its core billions of years ago. When galaxies merge, their central black holes eventually spiral together, but this process takes eons, and in the interim, the black holes can carve out separate domains of influence. In Andromeda's case, the intruder's black hole might have settled into an eccentric orbit around the primary, shepherding a cluster of stars into its own luminous entourage. This would explain the second peak's off-center position, a cosmic freeze frame of a slow-motion merger still in progress. But there's a twist. The fainter of the two peaks isn't just an orbiting interloper, it's lopsided. Hubble observations reveal its stars aren't evenly distributed, but clumped in a lopsided disk that wobbles like a spinning top losing momentum. This asymmetry suggests turbulent dynamics at play, possibly caused by the gravitational tug of war between the two nuclei. Some models even propose the secondary peak isn't a separate black hole at all, but a dense stellar stream stretched into a disk-like shape by the primary black hole's gravity, like taffy pulled thin between two hands. Then comes the wild card, the possibility of a black hole binary. If both peaks do harbor supermassive black holes, they'd be locked in one of the closest such pairings ever observed. Normally, black holes this massive, together weighing over 200 million suns, should either merge quickly or fling each other apart through gravitational recoil. Yet here they are, maintaining an improbable equilibrium. Their coexistence hints at unseen forces, perhaps dark matter or gas dynamics, acting as cosmic referees to keep the balance. The implications ripple far beyond Andromeda. If its double nucleus proves to be a stalled merger, it offers a rare glimpse into the messy middle stages of galactic collisions, a process usually observed either before impact or long after. It's like catching a tree halfway through falling, frozen mid-snap by some invisible hand. By studying this celestial standoff, we're witnessing the universe's most violent rearrangement in extreme slow motion, a dance that could last billions of years before reaching its crescendo. Yet the most tantalizing clue lies in what's not there. High-resolution infrared scans reveal a startling lack of young stars near the nuclei, suggesting Andromeda's core is unusually quiet for its size. This star formation drought might be the smoking gun of past turbulence, proof that the same gravitational forces carving the double nucleus also swept the area clean of star-forming gas. It's a cosmic catch-22. The very process that created this dazzling structure may have also sterilized its surroundings, leaving behind a glittering fossil of ancient violence. As we unravel Andromeda's two-hearted mystery, we're forced to confront how much we still don't understand about galactic centers. The rules we've written for black holes and mergers seem to bend here, reminding us that even the universe's most familiar objects can harbor startling secrets. And with Andromeda on a collision course with the Milky Way, its double nucleus isn't just a curiosity, it's a preview of the fate awaiting our own galaxy's core, a whisper from the future written in starlight. The Triangulum galaxy shouldn't be this twisted. As the third largest member of our local group, M33 is a classic spiral galaxy, or at least it's supposed to be. But peer closely and its disk tells a different story. Instead of lying flat like a spinning coin, it bends and warps at the edges, as if some invisible hand crumpled its outer reaches. This distortion isn't random. It's a cosmic fingerprint revealing a history of gravitational tugs of war with its colossal neighbors, Andromeda and the Milky Way. And hidden in those subtle twists are clues about the dance of galaxies on scales we're only beginning to map. Galactic warps aren't uncommon, most spirals show some bending at their edges. But Triangulum's distortion is extreme, with entire spiral arms flaring upward on one side and downward on the other, like a vinyl record left too close to a heat source. The culprit, gravity's relentless pull. Every time Triangulum swings close to Andromeda, its massive neighbor just 2.7 million light-years away, Andromeda's gravity yanks on its disk, stretching stars and gas into this lopsided shape. Think of it like tides on Earth, where the moon's pull distorts our oceans, but on a scale so vast it reshapes entire galaxies over eons. But here's where it gets stranger: the warp isn't static. Observations reveal its precessing, slowly wobbling like a spinning top losing momentum. This motion locks in a precise timeline of past encounters. By measuring the wobble's speed, astronomers can trace Triangulum's orbital history, pinpointing when it last had a close brush with Andromeda. The data suggests a dramatic flyby roughly 1 billion years ago, a cosmic near-miss that sent shockwaves through Triangulum's structure. Yet there's a discrepancy. The warp scale implies even stronger interactions, hinting at unseen players in this gravitational drama. That missing piece might be the Milky Way. Recent simulations show our galaxy's gravitational field, though more distant, could be compounding the distortion. As Triangulum orbits Andromeda, it also feels subtle tugs from us, adding extra torque to its already strained disk. It's a three-body problem playing out across millions of light-years, with each galaxy's pull leaving its mark on Triangulum's shape. Some researchers even speculate that dark matter filaments, the invisible scaffolding connecting galaxies, might be amplifying the effect, creating a web of forces that's bending the disk in ways pure gravity can't fully explain. The most astonishing clue lies in Triangulum's star-forming regions. While most warped galaxies see their outer gas too disrupted for robust starbirth, M33's twisted edges blaze with young blue stars. This suggests its warp is unusually gentle, leaving enough gas intact to keep stellar nurseries active. One theory posits that Triangulum's dark matter halo, its invisible gravitational anchor, is exceptionally spherical, cushioning the disk from the worst of the tidal strains. If true, it'd mean the galaxy's warp isn't a sign of damage, but resilience, a delicate balance between distortion and regeneration that keeps its star factories humming even under siege. What makes this warped disk so invaluable isn't just the story it tells about Triangulum, it's a window into galactic interactions everywhere. Most universe simulations treat galaxies as isolated islands, but Triangulum's distortion proves they're constantly reshaping each other, their histories written in bent starlight. By decoding its warp, we're not just studying one galaxy's fate. We're learning how all galaxies twist, stretch, and survive in a cosmos where no island truly stands alone. The large Magellanic Cloud is no stranger to cosmic fireworks, but one structure stands out even among its dazzling tapestry of star-forming regions, LMC4, a colossal bubble of gas so vast it could swallow our entire solar system 1,000 times over. This supergiant shell, stretching over 600 light-years across, isn't just a static remnant of stellar violence. It's a dynamic, evolving force reshaping its corner of the galaxy. Picture a soap bubble blown by the universe itself, its delicate surface shimmering with the energy of countless supernovae, except this bubble is made of searing plasma, swirling magnetic fields, and enough raw power to birth new stars even as it erases others from existence. What makes LMC-4 extraordinary isn't just its size, but its origin story. Most interstellar bubbles are blown by a single massive star's winds or the explosive death of one supernova. This shell, however, is the collective work of generations, dozens of supernovae detonating in waves over millions of years, each blast adding energy to the expanding shockwave. The result is a cosmic pressure cooker where gas is compressed, heated, and flung outward in intricate filaments. Infrared and radio observations reveal the shell's interior is cavernous, a near vacuum cleared by the combined force of these explosions, while its edges glow with the telltale signatures of ionized hydrogen and heavy elements forged in stellar furnaces. But LMC-4 isn't just destroying, it's creating. Along its turbulent rim, gas piles up in dense knots, collapsing under its own gravity to ignite new stars. These stellar newborns are often more massive and hotter than average, their fierce radiation sculpting the surrounding gas into surreal pillars and arches. It's a galactic feedback loop. The deaths of ancient stars trigger the births of new ones who will eventually explode to fuel the next cycle. This process isn't neat or orderly. Hubble images show the shell's surface pocked with smaller bubbles and cavities, evidence of younger supernova adding fresh chaos to the mix. The shell isn't a single structure so much as a living, breathing ecosystem of destruction and rebirth. The most tantalizing clue to LMC-4's power lies in its motion. Spectroscopic data reveals the shell isn't expanding evenly. Some regions race outward at over 50 kilometers per second, while others lag behind, trapped in dense interstellar gas. This lopsided growth suggests the shell is punching through the galaxy's uneven medium like a bulldozer plowing through hills and valleys. In some places, it's even broken through entirely, venting its hot interior into the surrounding space like a ruptured pressure valve. These breaches create chimneys, channels through which energy and metals escape into the wider galaxy, seeding future generations of stars with the recycled remains of their ancestors. Yet LMC-4's greatest impact might be invisible. Theoretical models suggest such supergiant shells play a crucial role in regulating galaxies' evolution. By carving out vast cavities, they limit where and how stars can form, effectively dictating a galaxy's structure over cosmic time. The energy they inject into interstellar space can stifle star formation in one region while jump-starting it in another, creating a patchwork of activity that defines a galaxy's character. In the case of the large Magellanic Cloud, LMC-4 is just one of many such shells, a single thread in a web of overlapping bubbles that together orchestrate the galaxy's rhythm of life and death. Standing back, the full picture emerges. LMC-4 isn't an anomaly or a spectacle. It's a fundamental force of galactic ecology, as essential to its environment as wind and rain are to Earth's climate. Its story reminds us that even the most violent events in the cosmos are part of a grander balance, a cycle where destruction and creation are two sides of the same coin, and where the echoes of ancient explosions still shape the universe's future. The small Magellanic Cloud has always been the scrappy underdog of the local group, a disorganized tangle of gas and stars barely holding itself together. But its most striking feature isn't the chaos at its core. It's the bizarre, wing-like structure stretching from its eastern flank, a graceful arc of stars and gas that seems utterly out of place against the galaxy's otherwise ragged silhouette. This so-called wing isn't just a chance alignment. It's a cosmic wound, a scar left by a gravitational brawl with its larger neighbor, the large Magellanic Cloud, and it's revealing secrets about how galaxies bleed stars into the void. When astronomers first mapped the wing's trajectory, They expected to find a simple tidal tail, the kind of elongated debris stream typical of galactic collisions. Instead, they uncovered a structure defying easy explanation. The wing arcs backward, almost curling in on itself like a ribbon caught in the wind, its stars moving in unison at speeds that don't match the rest of the small Magellanic Cloud. Even stranger, the gas within it is twisted into intricate filaments, as if sculpted by invisible hands. This isn't just a fragment torn loose, it's a galactic limb wrenched out of place and frozen mid-motion, a snapshot of violence preserved for millions of years. The culprit, a near miss with the large Magellanic Cloud roughly 200 million years ago. Simulations show the larger galaxy's gravity didn't just pull material away. It stirred the small Magellanic Cloud's gas like a spoon in coffee, triggering shockwaves that compressed gas clouds and ignited bursts of star formation. The wing's youngest stars are clustered along its spine, their blue-hot brilliance tracing the path of this ancient collision. But here's the twist: these stars shouldn't exist. The gas torn loose in such encounters is usually too diffuse to collapse into new stars, yet the wing's stellar nurseries are thriving, suggesting the collision funneled material into dense enough pockets to defy the odds. Deeper observations reveal an even stranger detail: the wing isn't just drifting away. Its base remains tenuously connected to the small Magellanic Cloud, as if the galaxy is reluctant to let go. This lingering attachment challenges our understanding of tidal forces, hinting that some galaxies might cling to their stolen material far longer than models predict. Some researchers speculate magnetic fields embedded in the gas could be acting like cosmic glue, resisting total separation. Others propose the small Magellanic Cloud's dark matter halo is stretching along with the wing, its invisible tendrils anchoring the structure against complete disintegration. The wing's ultimate fate is another mystery. Unlike typical tidal tails which disperse into invisibility, this structure shows signs of cohesion. Its stars share chemical signatures distinct from both the small Magellanic Cloud and the large Magellanic Cloud, suggesting they've mixed into something new, a hybrid population born from the collision. There's even evidence the wing is seeding its own tiny star clusters, like droplets breaking off a waterfall. If true, it could mean galactic collisions don't just destroy, they create entirely new stellar ecosystems in the debris. What makes the wing so much more than a cosmic curiosity is what it tells us about the fragility of small galaxies. The small Magellanic Cloud is being dismantled piece by piece, its stars siphoned away not just by the large Magellanic Cloud, but by the Milky Way's relentless gravity. The wing is merely the most visible symptom of this decay, a preview of what happens when dwarfs dance too close to giants. Yet even in its destruction, it offers a gift, a chance to study the mechanics of galactic interactions with unmatched clarity. Every star, every wisp of gas in that graceful arc is a data point, revealing how the universe reshapes its inhabitants, one gravitational tug at a time. Buried deep within the otherwise unremarkable Fornax dwarf galaxy lies something utterly perplexing. A massive, invisible knot of dark matter drifting through space with no stars to call its own. This isn't just another patch of the mysterious substance that permeates galaxies. It's a rogue clump denser than expected, floating like a ghostly iceberg in a cosmic sea. What makes it extraordinary isn't just its presence, it's the fact that it's untethered, a dark matter blob drifting freely, unanchored by the gravitational pull of stars or gas. Normally, dark matter and visible matter coexist in a delicate gravitational dance. Stars form within dark matter halos, their movement dictated by this invisible scaffold. But in Fornax, the rules seem broken. Observations reveal a concentrated pocket of dark matter offset from the galaxy's visible stars, as if someone sliced the shadow away from its source. This isn't just unusual, it's unprecedented. Imagine a marionette puppet still moving after its strings were cut, performing without a puppeteer. That's the level of defiance we're dealing with here. How could such a structure form? One theory suggests a violent past, an ancient collision that sent the galaxy's stars and dark matter reeling in opposite directions. Simulations show that when dwarf galaxies brush past larger neighbors, their dark matter can be stripped away, leaving behind isolated clumps. But Fornax's blob is too dense, too coherent for this explanation alone. Another possibility is even stranger. Dark matter might interact with itself in ways we don't yet understand. If certain dark matter particles experience friction or collisions, they could clump independently of stars, forming structures that float like invisible islands in space. The implications are staggering. If dark matter can exist in isolated, starless blobs, it could mean our universe is threaded with unseen structures, cosmic ghosts weaving through the emptiness between galaxies. Some theorists speculate these blobs might even be the seeds of future galaxies, waiting for gas to fall into their gravitational wells. Others warn they could distort our maps of the cosmos, skewing measurements of galactic mass and motion. Yet the most tantalizing clue lies in what's not there. The absence of stars in this blob challenges our fundamental ideas about galaxy formation. If dark matter can exist in such pure, unlit forms, it forces us to reconsider how galaxies assemble or fail to. Fornax's dark matter blob isn't just a curiosity. It's a cosmic riddle whispering that the universe's invisible machinery might be far more complex and far stranger than we ever imagined. The Sculptor dwarf galaxy isn't just orbiting the Milky Way, it's breaking every rule of galactic motion. While most of our galaxy's satellites circle in a neat, flat plane like planets around the Sun, Sculptor cuts a wild, perpendicular path, slicing through the Milky Way's poles like a daredevil comet on a cosmic joyride. This polar orbit isn't just unusual, it's a flagrant defiance of how satellite galaxies are supposed to behave, and it holds tantalizing clues about the hidden forces shaping our galactic neighborhood. Most dwarf galaxies orbiting the Milky Way conform to a predictable pattern, tracing elliptical paths aligned with our galaxy's disk. This isn't coincidence, it's physics. When smaller galaxies fall under the sway of a giant like the Milky Way, their orbits tend to flatten over time, conforming to the gravitational tug of the host galaxy's spinning mass. But Sculptor didn't get the memo. Hurtling around the Milky Way's poles at nearly 200 kilometers per second, it follows a trajectory so steep, it's like watching a pendulum swing at right angles to gravity. The question isn't just how this happened, it's what could possibly maintain such a radical orbit against the universe's relentless pull toward order. One explanation rewinds the clock to the early universe, when the Milky Way was still assembling its satellite entourage. Simulations suggest Sculptor might be a latecomer, a cosmic hitchhiker that arrived long after the Milky Way's main satellite plane had already formed. Instead of being born from the same primordial gas cloud as most Milky Way companions, it could have fallen into our gravitational grip from an unexpected angle, preserving its off-kilter path like a stone skipping across a pond at just the right trajectory. Supporting this idea, Sculptor's stars are older and more metal-poor than most satellites, hinting it originated in a quieter, more isolated corner of the cosmos before being captured. But there's a darker twist literally. The Milky Way's dark matter halo isn't smooth and symmetrical like a beach ball. It's lumpy, riddled with invisible density variations. Some theorists propose that Sculptor's polar orbit traces the contours of these hidden irregularities, following a gravitational groove carved by dark matter's uneven distribution. Imagine rolling a marble around the rim of a warped bowl. It might stabilize at strange angles dictated by the imperfections. Sculptor could be doing the same on a galactic scale, its path locked into place by the unseen topography of dark matter. Then there's the wild card, past encounters. The Milky Way's gravitational field isn't static. It's been jostled by collisions with other galaxies over billions of years. One particularly dramatic encounter, perhaps with the large Magellanic Cloud or a long-vanished dwarf, might have yanked the Milky Way's gravitational field sideways, tilting the very framework Sculptor orbits within. Like a passenger on a suddenly lurching train, the dwarf galaxy would have found itself flung onto a new path without changing its own motion. This could explain why its orbit appears so misaligned with the Milky Way's current orientation. It's orbiting the ghost of an earlier, differently angled gravitational field. Sculptor's rebellious path isn't just a celestial oddity, it's a stress test for our understanding of galactic dynamics. Every time it swoops past the Milky Way's poles, it challenges our models of how gravity behaves on vast scales. Its orbit is a cosmic fossil, preserving a record of ancient gravitational disturbances we can't observe directly. And as we decode its motion, we're not just studying one small galaxy's journey, we're reconstructing the Milky Way's violent, chaotic past, one radical orbit at a time. The Leo 1 dwarf galaxy isn't just moving, it's practically fleeing. Clocked at speeds topping 200 kilometers per second, this compact stellar system races through space with such velocity that astronomers are questioning whether it's even truly bound to the Milky Way at all. Most satellite galaxies orbit our cosmic neighborhood at more sedate paces, their trajectories neatly curved by the Milky Way's gravitational pull like marbles rolling around a bowl. But Leo 1 behaves more like a stone skipped across a pond, its path so fast and flat that it might eventually escape our galaxy's grasp entirely. What makes this speed demon so puzzling isn't just the raw velocity, it's the implications. For a galaxy of Leo 1's modest size to achieve such momentum, something must have given it an extraordinary gravitational kick. The leading theory points to a dramatic event in the distant past, a close encounter with the Milky Way's dark matter halo. Imagine swinging a ball on a string and suddenly releasing it. That sudden detachment sends the ball flying. Similarly, if Leo 1 once dove too deep into the Milky Way's invisible gravitational field, the resulting slingshot effect could have hurled it outward at these extreme speeds. Yet there's a wrinkle in this explanation. Detailed orbital reconstructions suggest Leo 1 might never have come close enough to the Milky Way to receive such a boost. This raises the tantalizing possibility that its speed isn't from our galaxy at all, but from an entirely different source, perhaps an ancient collision with another dwarf galaxy, or even a brush with the mysterious gravitational tides of the local group itself. The galaxy's chemical makeup adds another layer to the mystery. Unlike most Milky Way satellites, Leo 1 stars show surprising metallicity for their age, hinting at a past rich with stellar explosions that could have provided enough energy to alter its trajectory fundamentally. The stakes of this velocity riddle extend far beyond one small galaxy. If Leo 1 does break free, it would be among the first documented cases of a dwarf galaxy escaping its host, a real-time test of our models for how galactic relationships dissolve. Alternatively, if it remains bound despite appearances, it would force us to reconsider the Milky Way's total mass, potentially revealing hidden reservoirs of dark matter extending far beyond current estimates. Every measurement of its accelerating path is like reading a cosmic speedometer calibrated to the invisible forces shaping our corner of the universe. Perhaps most intriguing is what this means for the concept of galactic loyalty. In a universe where gravity typically dictates strict hierarchies, small galaxies orbiting large ones, which in turn orbit even larger clusters, Leo 1's rebellious speed challenges the assumption that cosmic structures are permanent. Its trajectory suggests a temporary alliance rather than eternal fealty, a reminder that even in the seemingly rigid architecture of the cosmos, everything is ultimately in motion and nothing is forever. As it streaks across the void, this galactic renegade forces us to confront an unsettling truth. Our Milky Way's dominion may not be as absolute as we once believed. The Leo 2 dwarf galaxy holds a secret in its starry fabric. Gaps, not the kind left by missing puzzle pieces, but vast, eerie regions where stars simply refuse to cluster. While most galaxies scatter their stars in smooth gradients or dense knots, Leo 2's stellar population looks like Swiss cheese, pockmarked with voids that defy explanation. These aren't random absences, they're structured, almost deliberate, as if some cosmic hand reached in and scooped out handfuls of stars with surgical precision. What could carve such voids into a galaxy? The prime suspect is gravity specifically, the gravitational bullying of larger galaxies like the Milky Way. As Leo 2 orbits our galaxy, tidal forces stretch and compress its stars, much like the moon's pull distorts Earth's oceans. But here's the twist: instead of leaving behind messy, chaotic trails, these tides seem to have sculpted clean, starless pockets. Simulations suggest this happens when Leo 2's orbit brings it close enough for the Milky Way's gravity to resonate with specific frequencies within the dwarf, creating standing waves that push stars out of certain zones while piling them into others. Imagine shaking a box of sand. Some areas clump together while others go curiously bare. But there's a darker possibility. These gaps might be the fingerprints of an ancient massacre, the aftermath of a long-lost smaller galaxy that Leo 2 devoured billions of years ago. When galaxies merge, the victim stars don't just blend in seamlessly. They're strewn along chaotic orbits, leaving behind underdense regions as they're torn apart. The chemistry of Leo 2's stars supports this. Some have unusual metal ratios, hinting at an exotic origin. If true, those gaps aren't just empty space, they're celestial crime scenes, marked by the absence of stars that once belonged to another galaxy entirely. What makes these voids so valuable isn't just their mystery, it's their defiance of time. Unlike tidal tails or streams, which fade as stars disperse, gaps can persist for billions of years, preserving a record of events long after more obvious traces have vanished. They're like fossilized footprints in the stellar sand, offering clues about the Milky Way's past interactions without a single word. And as we map them in ever greater detail, we're not just studying Leo 2's structure, we're decoding a gravitational language written in negative space where emptiness speaks louder than light. Yet the most tantalizing question remains: could these gaps hide more than just missing stars? Some theorists speculate they might be nurseries for dark matter substructures, invisible clumps whose gravity cleared out the stars but left no visible trace. If so, Leo 2's voids aren't just relics, they're windows into the universe's unseen architecture, where the true rulers of gravity lurk in the dark, shaping galaxies from the shadows. The Ursa Minor dwarf galaxy is playing a cosmic shell game with dark matter, and astrophysicists are scrambling to spot the trick. At first glance, this faint satellite of the Milky Way appears unremarkable, just another ancient metal-poor dwarf drifting through the galactic halo. But peer into its gravitational profile and something bizarre emerges. Unlike nearly every other galaxy observed, Ursa Minor's dark matter density doesn't spike at its core. Instead, it flattens into what astronomers call a core distribution, as if some unseen force scooped out the dark matter from its center like the pit of an avocado. This isn't just a minor anomaly, it's a direct challenge to our most fundamental models of how dark matter behaves. Simulations of cosmic structure formation have long predicted that dark matter should pile up densely in galactic centers, forming what's known as a cuspy profile. These theoretical models, like the famous Navarro-Frank-White profile, suggest dark matter halos should be steeply concentrated, with density rising sharply toward the core. Yet Ursa Minor flips this expectation on its head. Its stars move as if the galaxy's gravitational pull weakens toward the center, behavior that only makes sense if the dark matter is distributed in this counterintuitive, flattened arrangement. Imagine swinging a lasso around a pole, only to find the rope goes slack as you get closer. That's the gravitational paradox at play here. One possible explanation involves the messy reality of galactic interactions. When dwarf galaxies like Ursa Minor orbit larger hosts, they don't just glide peacefully, they're subjected to brutal tidal forces. The Milky Way's gravity can act like a cosmic spatula, scraping away outer layers of stars and dark matter with each close pass. Some theorists propose these repeated gravitational assaults might have stirred Ursa Minor's dark matter, redistributing it from the center outward. It's a process akin to shaking a snow globe. The flakes, or in this case, dark matter particles, get dispersed evenly rather than settling in a pile. Supporting this idea, Ursa Minor's orbit brings it perilously close to the Milky Way's disk, making it prime real estate for such tidal disruption. But there's a catch. Other dwarf galaxies with similar orbits don't show this chord profile, and simulations struggle to reproduce such extreme flattening without completely destroying the galaxy. This has led to more radical proposals. Perhaps dark matter isn't the simple, collisionless substance we've assumed. Some models suggest dark matter particles might interact with each other through unknown forces, creating a kind of pressure that resists central condensation. Think of it like gas in a balloon. Instead of collapsing inward, mutual interactions could keep the dark matter puffed up. Alternative theories go even further, proposing modifications to Newtonian gravity itself, though these remain contentious. The stakes of this mystery extend far beyond one small galaxy. If Ursa Minor's chord profile stems from dark matter's intrinsic properties, it could reveal entirely new physics hiding in plain sight. But if tidal forces are responsible, we need to understand why they affect some galaxies and not others, a puzzle that could reshape our view of galactic evolution. Every new observation tightens the constraints, yet Ursa Minor's dark matter remains an enigma, its flattened core standing as both a challenge and an invitation to look deeper, question harder, and reconsider what we think we know about the invisible scaffolding of the universe. The Draco dwarf galaxy has a gravitational grip that defies logic. Its stars cling together with the tenacity of a swarm of fireflies trapped in cosmic amber. This unassuming satellite of the Milky Way, barely 1% the mass of our galaxy, packs its stellar population into a space so dense it rivals globular clusters in sheer tightness. By all accounts, such a small galaxy shouldn't possess the gravitational muscle to keep its stars this compact. Yet here they are, orbiting in a sphere so rigidly organized, it's as if the entire system has been shrink-wrapped by invisible hands. What makes Draco's stellar lockdown so puzzling is the absence of visible scaffolding. Most galaxies this small rely on dark matter to anchor their stars, but Draco's dark matter halo is oddly lackluster, too diffused to explain the ferocity of its gravitational binding. This suggests something else is at play, a hidden mechanism corralling these stars with precision. One theory points to Draco's ancient origins. Formed over 13 billion years ago, it's among the universe's oldest galactic fossils, a relic from an era when gas clouds collapsed into stars with unrivaled efficiency. Without the heavy elements that scatter modern star-forming regions, primordial gas may have condensed into hyper-dense clusters, birthing stars already locked into orbits tighter than a drum. But there's another twist. Draco's stars aren't just packed tightly, they move in eerie synchrony. Unlike the chaotic orbits seen in younger dwarfs, these ancient stars glide around the galaxy's core as if choreographed, their paths intersecting with uncanny precision. This suggests the galaxy's gravitational field isn't just strong, it's impeccably smooth, free of the lumps and bumps that typically scatter stellar trajectories. Some astronomers speculate Draco's dark matter, though sparse, might be distributed in an unusually uniform shell, creating a gravitational cushion that keeps stars evenly spaced. Others propose its stars are all that remain of a far larger galaxy, the sole survivors of a catastrophic encounter that stripped away everything else, leaving only this dense core behind. The most tantalizing clue comes from Draco's uncanny silence, its complete lack of young stars or gas. This isn't just a dormant galaxy, it's a stellar graveyard frozen mid-collapse. Without fresh material to stir the pot, Draco's stars have settled into an equilibrium so stable it's practically self-sustaining. Picture a pendulum that, once set swinging, never loses energy. Only here, the pendulum is tens of thousands of stars locked in an endless dance. Yet this perfect balance raises a paradox. If Draco's gravity is this potent, why hasn't it pulled in stray gas or neighboring stars over billions of years? The answer might lie in its orbit, a wide, slow loop around the Milky Way that spared it from the tidal disruptions that typically feed galaxies fresh material. Like a hermit who's barred the door, Draco has kept the cosmos out, preserving its pristine stellar prison against all odds. As we unravel Draco's secrets, we're forced to reconsider the rules of galactic survival. This tiny galaxy isn't just an outlier. It's a time capsule proving that in the cosmos, size isn't everything. Sometimes the smallest structures wield the most surprising gravitational might. The Sextans dwarf galaxy is hiding a secret one that stretches far beyond the faint smudge of stars we see through telescopes. While most galaxies wear their dark matter like a close-fitting cloak, Sextans has thrown its invisible shroud wide open, with a halo of dark matter extending up to 10 times farther than its visible stellar boundary. This isn't just an oversized accessory, it's a cosmic anomaly, a ghostly embrace so vast it defies everything we know about how dark matter should behave in small galaxies. Picture a city where the streetlights only illuminate a few blocks, but the shadows of unseen skyscrapers stretch for miles beyond. That's Sextans' paradox, a galaxy where the invisible scaffolding dwarfs the visible structure. Normally, dwarf galaxies have dark matter halos that taper off gently, their gravitational grip weakening as you move outward. But here, the halo clings stubbornly to its outermost reaches, as if some unseen force is propping it up against cosmic erosion. The stars, by comparison, seem like an afterthought, huddled in the center while dark matter dominates the outskirts. What makes this extended halo so puzzling isn't just its size, it's the way it contradicts the rules of galactic survival. Dwarf galaxies orbiting giants like the Milky Way are supposed to get stripped of their dark matter over time, their outer layers peeled away by tidal forces. Sextans, though, has somehow preserved its phantom halo against all odds. One theory suggests its dark matter might be fluffier than usual, less prone to clumping, making it harder for tidal forces to tear away. Imagine trying to pluck feathers from a dandelion versus a pine cone. The former resists disruption because its structure dissipates the pull, but there's a darker possibility. Sextans' halo might not be primordial at all. It could be a cosmic illusion stretched by an ancient encounter with the Milky Way. Simulations show that when a small galaxy swings too close to a larger one, its dark matter doesn't just vanish, it gets smeared into elongated streams like taffy pulled thin. If Sextans once ventured perilously close to our galaxy, its halo could have been yanked into this exaggerated shape, frozen in place as a gravitational scar. Supporting this idea, the galaxy's stars show subtle signs of disturbance, as if their quiet orbits were once violently interrupted. The most tantalizing clue, though, comes from what Sextans doesn't have: gas. Unlike other dwarfs with extended dark matter, Sextans is bone dry, its reservoirs of star-forming fuel long since stripped away. This suggests its dark matter halo might be acting like a cosmic shield, sheltering the galaxy's core while sacrificing its outer gas to the Milky Way's hunger. It's a trade-off: lose the fuel for new stars, but keep the invisible scaffolding that holds everything together. Yet the implications ripple far beyond Sextans. If dark matter can stretch this far without collapsing, it challenges our models of how galaxies form and evolve. Perhaps what we're seeing isn't an anomaly, but a hidden phase of galactic life, one where dark matter lingers like a ghost long after the visible galaxy has faded. Or maybe Sextans is a cosmic rebel, revealing that dark matter's behavior is far more complex than our simulations predict. every observation peels back another layer, exposing just how much we still don't know about the invisible hands shaping the universe. And so, the Sextans dwarf stands as a silent sentinel at the edge of understanding, its dark halo a reminder that even in the smallest galaxies, the deepest mysteries dwell not in the light we see, but in the shadows we're only beginning to trace. The Carina dwarf galaxy is a cosmic chronicle written in starlight, a place where time doesn't flow smoothly but instead arrives in sudden, violent bursts. Unlike most galaxies that form stars at a steady trickle, Carina's history is carved into distinct chapters, each separated by billions of years of eerie silence. Imagine a volcano that erupts cataclysmically once every few millennia, then falls dormant without warning. That's the rhythm of creation in this enigmatic dwarf galaxy. The evidence is etched into Carina's color magnitude diagram, a kind of stellar census that reveals the ages of its stars. Instead of a smooth distribution, the data shows sharp peaks, 3 to be exact, like spikes on a seismograph recording ancient tremors. The first burst happened around 13 billion years ago, when the universe itself was still in diapers. Stars from this epoch glow faint and red today, their light weathered by time. Then, inexplicably, Carina fell silent for nearly 6 billion years, a pause so long, it spans half the age of the cosmos. When star formation finally reignited 7 billion years ago, it did so with vigor, birthing a generation of stars richer in heavy elements than their predecessors. Then another hiatus. The final burst occurred a mere 2 billion years ago, leaving behind clusters of young, blue stars that stand out like sapphires against the galaxy's ancient crimson backdrop. What could trigger such erratic behavior? The leading theory points to Carina's turbulent dance with the Milky Way. Every time this dwarf galaxy swings close to our own, the gravitational encounter might compress its gas, squeezing it just enough to ignite a new wave of star formation. But here's the puzzle. Other dwarf galaxies on similar orbits don't show this staggered rhythm. Carina's pauses are too precise, too cleanly separated to be random. Some astronomers suspect its dark matter halo plays a role. Its gravitational pull could act like a cosmic throttle, allowing gas to accumulate only at specific intervals. Others propose that Carina's gas reservoir isn't being stripped away entirely but cyclically expelled and recaptured, like a fountain spraying water upward only to catch it again. Then there's the wild card, internal dynamics. Carina's own supernova might be both midwife and executioner to its stellar generations. Each burst of star formation would eventually produce massive stars that explode, their shockwaves blowing away the remaining gas and shutting down further starbirth until gravity slowly gathers enough fuel to begin anew. This feedback loop could explain the long delays galactic physics hitting the reset button over and over. But the most tantalizing clue lies in Carina's chemical fingerprint. The stars from each epoch carry distinct elemental signatures like geological strata recording Earth's history. The oldest stars are metal poor, forged from nearly pure hydrogen and helium. Those from the second burst show traces of heavier elements: carbon, oxygen, iron, the debris of the first generation's explosive deaths. The youngest stars are richer still, proving Carina didn't just wake up periodically. It evolved, learning to recycle its material more efficiently with each rebirth. This isn't just a story about one small galaxy, it's a challenge to our understanding of how galaxies live and grow. Carina's stuttering star formation suggests the universe doesn't always follow a smooth narrative. Sometimes it writes in fits and starts, leaving behind cryptic gaps that force us to rethink the rules. And as we decode its erratic timeline, we're reminded that even the quietest corners of the cosmos can harbor the most unpredictable rhythms. The Antlia II galaxy is the cosmic equivalent of a ghostly whisper, so faint, so diffuse, it barely registers as a galaxy at all. Its stars aren't clustered tightly like most galactic communities, but scattered so sparsely that the entire structure glows with the luminosity of a single dim star cluster stretched across an unthinkable 20,000 light-years. If the Milky Way is a bustling metropolis, Antlia 2 is a handful of lanterns lost in an endless desert, their light swallowed by the void between them. This extreme diffuseness isn't just unusual, it's a direct challenge to our understanding of how galaxies hold themselves together. What makes Antlia 2's fluffy composition so baffling is the sheer scale of its emptiness. Normally, galaxies, even small, fragile dwarfs, maintain some gravitational cohesion, their stars orbiting within a well-defined sphere or disk. But Antlia 2's stars drift so far apart, they move more like solitary travelers in deep space than members of a unified system. Measurements reveal its surface brightness is 5,000 times fainter than the Milky Way's disk, so dim that astronomers almost missed it entirely when scanning the sky. It's as if someone took a typical dwarf galaxy and turned down the density slider to near zero, leaving behind a skeletal outline of what a galaxy ought to be. The leading theory for this eerie dispersal involves a cosmic tug-of-war with the Milky Way. As Antlia 2 orbits our galaxy, tidal forces, the same gravitational stresses that create ocean tides on Earth, may have stretched it like taffy, pulling stars outward while dark matter, the invisible glue holding galaxies together, resisted the disruption. But here's the twist. Simulations show this process usually leaves galaxies more compact, not more diffuse. To explain Antlia 2's extreme fluffiness, some astrophysicists propose its dark matter halo might be unusually soft, lacking the dense core that typically anchors stars. Imagine a ball of cotton candy versus a marble. Both have mass, but one yields easily to pressure. If Antlia 2's dark matter is similarly malleable, it could explain why the galaxy puffed up instead of collapsing under tidal strain. Yet there's another possibility, even more intriguing. Antlia 2 might be a failed galaxy, a cosmic experiment that never quite got off the ground. In the early universe, clouds of gas needed a critical density of dark matter to collapse into stars. If Antlia 2 formed in a region where dark matter was too thinly spread, its gas might have coagulated into stars but never achieved the gravitational muscle to hold them close. This would make it a rare relic of a low-density universe, a place where the usual rules of galactic formation never fully applied. Supporting this idea, Antlia 2's stars are ancient and metal-poor, suggesting it's been languishing in this sparse state for nearly the entire age of the cosmos. The implications ripple far beyond this one ghostly galaxy. If Antlia 2's fluffiness stems from its unusual dark matter, it could hint at hidden diversity in how this mysterious substance clumps across the universe. Alternatively, if it's a fossil from an era of sparse galaxy formation, it might force us to revise our models of cosmic evolution. Every observation peels back another layer, revealing that even in our own local group, the universe still has surprises tucked away, whispers from the void that challenge everything we thought we knew. The Crater 2 dwarf galaxy moves through space with the grace of a dancer gliding across a perfectly smooth floor, its orbit around the Milky Way so circular, so unnervingly precise, it defies the chaotic ballet of most dwarf galaxies. While its siblings plunge in eccentric loops, swinging wildly close to our galaxy's core before hurtling back out into the void, Crater 2 traces a path as steady as a planet orbiting the Sun. This isn't just unusual, it's a cosmic contradiction, a small galaxy behaving with the poise of something far more massive, and it's forcing astronomers to question the very rules of galactic motion. What makes Crater 2's orbit so baffling is its icy composure. Most dwarf galaxies resemble comets, their paths stretched into elongated ellipses by the Milky Way's gravitational tides. Crater 2, though, maintains a distance of roughly 150,000 light-years at all times, never venturing too close or straying too far. This kind of equilibrium usually requires an extraordinary balancing act, a precise match between the galaxy's velocity and the Milky Way's pull. For something as small as Crater 2, achieving this balance should be statistically improbable, like rolling a marble into a bowl and having it circle the rim forever without dipping or flying off. One explanation lies in Crater 2's dark matter halo, or rather, the ghostly remains of it. Simulations suggest the galaxy may have once been far more massive, its original dark matter cushioning it against the Milky Way's disruptive forces. Over billions of years, tidal stripping could have whittled away its outer layers, leaving behind only this dense core on a perfectly circular orbit, like a peach pit preserved after the fruit has rotted away. If true, Crater 2 isn't just an oddball, it's a survivor, its current path a fossilized imprint of a long-lost gravitational struggle. But there's a darker, more tantalizing possibility. Crater 2 might be a passenger, not a prisoner. Some models propose it wasn't born in the Milky Way's gravitational grip at all, but arrived as part of a larger group, perhaps a retinue of the large Magellanic Cloud, our galaxy's most massive satellite. If Crater 2 once orbited the LMC before being wrested away by the Milky Way's gravity, its current path could be a cosmic handoff, a stable orbit inherited from its former host. This would explain its unnatural serenity, a vestige of a time when it danced to a different galactic tune. The implications ripple far beyond orbital mechanics. Crater 2's sedate journey challenges our understanding of how galaxies assemble. If its circular path stems from a stripped-down dark matter core, it suggests even the faintest dwarfs might hide dense invisible anchors we've overlooked. If it's a transferred satellite, it reveals how larger galaxies like the LMC can sculpt the orbits of their companions before surrendering them to giants like the Milky Way. Either way, Crater 2's cold, methodical motion isn't just a curiosity, it's a key unlocking secrets about the hidden forces that choreograph the cosmos. And so, this unassuming dwarf galaxy glides on, a silent rebel against the chaos of cosmic dynamics. Its orbit, so precise it feels almost artificial, reminds us that even in the violent swirl of gravity and motion, the universe sometimes finds moments of perfect, improbable balance. Every calculation, every simulation it defies, nudges us closer to rewriting the rules of galactic motion, one perfectly circular step at a time. The Tucana dwarf galaxy isn't just old, it's a living fossil, a preserved relic from a time when the universe was raw and untamed. Isolated over 2 million light-years from the Milky Way, this modest collection of ancient stars floats in the cosmic equivalent of a time capsule, untouched by the gravitational turbulence that's reshaped most galaxies over billions of years. While others merged, collided, and recycled their stars into newer generations, Tucana remained aloof, its stellar population frozen in a state that mirrors the cosmos's infancy. What makes Tucana's stars so extraordinary is their pristine composition. Unlike the Sun, which contains traces of heavier elements like iron and carbon forged in earlier stellar explosions, Tucana's stars are nearly pure hydrogen and helium, the raw materials of the Big Bang itself. It's as if this galaxy skipped the universe's recycling program entirely, preserving its first and only generation of stars like a snapshot of the early cosmic dawn. This metal pore signature is so rare that studying Tucana is like stumbling upon an untouched archaeological dig, where every layer tells an unfiltered story of how the first galaxies assembled. But isolation alone doesn't explain its fossil status. Tucana's quiet defiance of galactic evolution runs deeper. Most dwarf galaxies, even those far from major neighbors, experience sporadic bursts of star formation as they slowly consume their gas reserves. Tucana, though, appears to have exhausted its fuel in one initial, frenzied burst over 12 billion years ago, then shut down completely. Its star-forming factories didn't just pause, they closed permanently, leaving behind a stellar population so ancient they predate the formation of Earth's own building blocks. The mystery lies in why this shutdown was so absolute. One theory points to dark matter, or rather the lack of it. Tucana's gravitational grip is surprisingly weak for its size, suggesting its dark matter halo might be unusually sparse. Without the dense, invisible scaffolding that typically compresses gas into new stars, Tucana's fuel could have simply drifted away, escaping into intergalactic space like smoke from an extinguished fire. Alternatively, its own supernova might have blown out its remaining gas in a single, violent exhale, leaving the galaxy with no material for a second act. Yet the most tantalizing clue comes from Tucana's surroundings. Unlike other dwarf galaxies, which often trail streams of stolen stars or gas, Tucana's environment is eerily clean, no debris, no signs of past collisions. This suggests it wasn't just isolated, it was born isolated, possibly forming in a void-like pocket of the early universe where few other galaxies ever took root. If true, Tucana isn't merely a relic. It's a cosmic hermit, a galaxy that spent its entire existence in the universe's quietest neighborhood, untouched by the chaos that shaped everything else. And that's what makes it so invaluable. While telescopes like Hubble and JWST peer deep into the past to study ancient galaxies, Tucana offers something just as rare, a nearby, undisturbed example of the universe's primordial building blocks. Its stars are time machines, their light encoding the chemical fingerprints of an era before heavy elements existed, before galaxies grew large, before the cosmic web became crowded. By decoding them, we're not just studying a single dwarf galaxy, we're glimpsing the universe as it was before it learned how to build itself into what we see today. Tucana's silent endurance is a reminder that the cosmos doesn't always follow the script. While most galaxies are born, evolve, and die in cycles of creation and destruction, some, like this cosmic fossil, opt out entirely, choosing instead to linger as echoes of a simpler time. And in that refusal to change, they become our clearest window into the past. The Pegasus dwarf galaxy isn't just a quiet backwater. It's a cosmic pressure cooker, its gas clouds churning with violence that defies the galaxy's modest size. While most dwarf galaxies host placid reservoirs of hydrogen, Pegasus's interstellar medium resembles a storm-tossed ocean, its gas whipped into frothy turbulence by forces unseen. This isn't the gentle simmer of star formation, it's outright chaos, with gas velocities fluctuating so wildly they've left astronomers questioning what could possibly stir such frenzy in such a small galactic system. At the heart of the mystery lies the galaxy's supernova history. Massive stars live fast and die young, exploding in violent supernova that send shockwaves rippling through surrounding gas. In Pegasus, these explosions seem to have stacked like dominoes, each new detonation compounding the turbulence of the last. Radio telescopes reveal vast filamentary structures in the gas, the scars of ancient blasts, while younger star clusters appear to be forming inside bizarre, bubble-like cavities blown clear by more recent explosions. It's as if the galaxy is trapped in a cycle of self-destruction and rebirth, where each stellar death sows the seeds for the next generation. But supernova alone can't explain the scale of the disruption. Infrared observations show entire gas clouds moving in coordinated, large-scale flows, suggesting an external force is at work. The leading suspect, the Milky Way's gravitational tides. As Pegasus orbits our galaxy, it may be experiencing tidal shocks, gravitational jolts that compress and stretch its gas like taffy. These interactions could be amplifying the internal turbulence, turning what might have been localized stellar fireworks into a galaxy-wide maelstrom. Supporting this, the gas motions align suspiciously well with Pegasus's orbital path, as if the galaxy is plowing through an invisible barrier of dark matter, its gas shuddering from the strain. Yet there's a twist. Some of the most turbulent regions show no obvious connection to supernova or tides. Instead, they coincide with areas where Pegasus's magnetic fields are unusually strong. This raises the electrifying possibility that magnetism is playing puppeteer, twisting the gas into knots through forces we're only beginning to understand. Imagine holding a handful of iron filings near a magnet the way they leap into frantic alignment. Now scale that up to galactic proportions, with magnetic fields threading through the gas like invisible wires, guiding its motion in ways gravity alone cannot. The implications stretch beyond Pegasus. Turbulence like this isn't just spectacle, it's a galactic regulator controlling how and where stars form. In calmer galaxies, gas collapses smoothly into dense knots that ignite new stars. But Pegasus's gas is so violently stirred, it resists collapse like trying to light a candle in a hurricane. Paradoxically, this might explain why the galaxy's star formation is so patchy, with intense bursts in some regions and eerie voids in others. The turbulence isn't just a side effect, it's shaping the galaxy's very evolution. And so, the Pegasus dwarf stands as a testament to the universe's untamed side. Its seething gas clouds remind us that even the smallest galaxies can harbor forces of staggering power forces that don't just respond to the cosmos, but actively rewrite their own destinies through every shockwave, every magnetic twist, every tidal tremor. In their chaos, we're glimpsing the raw physics that govern all galaxies, just turned up to 11. The Wolf-Lundmark galaxy should be a retirement home for ancient stars, a quiet, fading dwarf where stellar nurseries shut down billions of years ago. Yet scattered across its ragged edges gleam brilliant blue stars, burning hot and young, like sparks from a fire everyone thought had long gone cold. These aren't just minor anomalies, they're cosmic rule breakers, challenging our assumptions about how small, isolated galaxies evolve. What makes these blue stars so baffling is their location. Wolf-Lundmark, or WLM for short, is one of the most isolated galaxies in the Local Group, drifting over 3 million light-years from the Milky Way's disruptive influence. Without nearby galaxies to stir its gas or trigger new star formation, WLM should have exhausted its fuel eons ago, leaving only the dim glow of aging red stars. Instead, its outer regions blaze with stellar newborns, their blue-white light cutting through the galaxy's otherwise ancient haze. It's like finding a bustling nursery in the middle of a ghost town, defying every expectation of how such places should behave. The secret might lie in WLM's pristine gas reserves. Unlike most dwarf galaxies, which get stripped of their star-forming material by larger neighbors, WLM's isolation has left its hydrogen untouched, a rare pocket of primordial fuel. Over billions of years, random fluctuations in this gas could have slowly clumped together, collapsing under their own gravity to ignite these late-blooming stars. But here's the twist: the blue stars aren't randomly scattered. They cluster in distinct knots, suggesting something more deliberate than chance collapse. Some astronomers propose that WLM's own supernova, though rare, might have acted as cosmic bellows, compressing gas clouds with their shock waves and triggering waves of starbirth long after the galaxy's prime. Then there's the dark matter factor. WLM's faint gravitational grip suggests its dark matter halo is unusually sparse, too weak to efficiently pull gas into star-forming regions on its own. Yet the blue stars exist, hinting at a delicate balance. Perhaps WLM's gas is so undisturbed that even the gentlest nudges, a passing cosmic ray, a subtle density wave, can tip it into collapse. It's a reminder that in the quietest corners of the universe, even whispers can spark creation. The implications ripple beyond WLM itself. These blue stars are time capsules, forged from gas nearly as pristine as the early universes. By studying their composition, we're glimpsing a process that might have been common 13 billion years ago when galaxies were first assembling. WLM isn't just an oddball, it's a portal, showing us how the cosmos builds stars when left to its own devices, far from the gravitational noise of larger neighbors. And in their defiant glow, we're forced to confront a humbling truth. even the oldest, loneliest galaxies still have surprises left to reveal. The IC-1613 galaxy is a cosmic metronome, its clockwork precision so exact, it's redefined how we measure the universe's vast distances. Unlike most galaxies shrouded in dust, IC-1613's interstellar environment is freakishly pristine, its gas and stars visible with a clarity that's almost unsettling. This transparency isn't just a curiosity, it's a scientific goldmine. Because here's the thing, when you're trying to pin down distances across millions of light years, even the tiniest obstructions can skew your measurements like a funhouse mirror. But IC-1613, it's the closest thing astronomy has to a perfectly calibrated ruler in the void. The secret lies in what's missing. Galactic dust, those microscopic particles of carbon and silicon floating between stars, normally scatters and dims starlight, forcing astronomers to guess how much brightness they're losing along the line of sight. It's like trying to judge the wattage of a lighthouse through fog. But IC-1613's dust content is so negligible, its stars shine with nearly unobstructed brilliance. This lets telescopes capture their true luminosities with unmatched precision, turning the galaxy into a laboratory for testing cosmic yardsticks. One method, the tip of the red giant branch, exploits the predictable brightness of aging red giant stars. These stellar retirees all peak at roughly the same intrinsic luminosity before flickering out, but only in dust-free environments like IC-1613 can we measure that peak without second-guessing. Then there's the Cepheid variable stars, cosmic lighthouses whose pulsations act as distance markers. Normally, dust complicates their signals, forcing astronomers to apply messy corrections. But in IC-1613, their light arrives undistorted, their pulse rates and brightnesses aligning so cleanly, they've become the benchmark for calibrating Cepheids elsewhere. This precision ripples across cosmology. When the Hubble Space Telescope measured IC-1613's distance down to a razor-thin margin of error, just 2.3% uncertainty, it didn't just map one galaxy. It tightened the screws on the entire cosmic distance ladder, the step-by-step method we use to measure everything from nearby stars to the edge of the observable universe. But the real breakthrough came when astronomers realized IC-1613's cleanliness wasn't accidental. Its lack of dust stems from a quirk of chemistry specifically, a shortage of heavy elements needed to form those light-scattering particles. This makes it a relic of the early universe, where galaxies hadn't yet cooked enough metals in their stellar furnaces to pollute their surroundings. By studying it, we're not just refining distance measurements, we're peering back to a time before cosmic recycling cluttered the skies. And that's what makes IC-1613 more than a tool, it's a Rosetta Stone. Every photon that reaches us from its crystal core environment carries purer data than we'd get from 100 dust-choked galaxies. In a field where a few percentage points of error can mean the difference between conflicting models of universal expansion, this unassuming dwarf galaxy is quietly resolving debates that have raged for decades. Its clarity isn't just a convenience, it's a revelation, proving that sometimes the most profound insights come not from the cosmos's grandest structures, but from its cleanest windows. The Phoenix Dwarf Galaxy should be a cosmic graveyard, a place where star formation flickered out billions of years ago, leaving behind only the dim embers of aging red stars. But against all odds, this ancient dwarf has reignited, blazing with newborn stars after a 10 billion-year silence. It's as if a long-dead campfire suddenly burst back to life, its flames defying every law of celestial thermodynamics. The question isn't just how this happened, it's what could possibly rekindle a galaxy's stellar engines after an eternity of dormancy. The first clue lies in the galaxy's hydrogen. Most dormant dwarfs lose their gas to supernova or galactic tides, leaving them bone dry. Phoenix, though, clung to wisps of primordial fuel, just enough to spark a late-breaking stellar renaissance when the conditions aligned. But here's the twist. This gas didn't come from Phoenix itself. Radio telescopes revealed delicate filaments of hydrogen stretching toward the galaxy like cosmic umbilical cords, suggesting it's been siphoning fuel from intergalactic space. Imagine a desert cactus drawing moisture from morning fog. Phoenix seems to have harvested just enough drifting gas to trigger a modest starburst, eking out one last generation of stars from the universe's leftovers. Yet gas alone doesn't explain the timing. Why now, after 10 billion years of stillness? The answer might involve a hidden dance with dark matter. Simulations show Phoenix's faint dark matter halo could have acted like a gravitational net, slowly accumulating stray hydrogen over eons until it reached a critical mass. Once enough gas pooled, even a minor disturbance, a passing cosmic ray, a ripple in the galactic magnetic field might have tipped the scales, compressing the fuel into dense enough knots to ignite. It's a reminder that in the cosmos, patience isn't just a virtue, it's a catalyst. Given enough time, even the faintest forces can conspire to rewrite a galaxy's fate. Then there's the wild card, stellar feedback. The galaxy's oldest stars, though feeble, still emit radiation and stellar winds. Over billions of years, this gentle pressure could have pushed remaining gas into sheltered pockets, where it lingered until the conditions were right to collapse. Think of it like cosmic composting, stellar remnants nurturing the seeds of their own successors. The resulting stars, though young, carry traces of Phoenix's ancient history in their chemical makeup, blending pristine hydrogen with whispers of heavier elements from long-dead ancestors. But the most tantalizing possibility is that Phoenix isn't unique. Across the local group, other dead dwarfs might be hovering on the edge of rebirth, their own starbursts waiting for the right cosmic nudge. If true, it means galactic evolution isn't a one-way street. Even in the quietest corners of the universe, the story of star formation might not have a final chapter, just long, unpredictable pauses between verses. And as we watch Phoenix's unexpected resurgence, we're glimpsing a truth far more profound. In the cosmos, endings are just beginnings in disguise. NGC 6822, better known as Barnard's Galaxy, holds a celestial treasure trove of cosmic anomalies, but none shine quite as strangely as its carbon stars. These crimson-tinged giants aren't just rare, they're stellar alchemists, their atmospheres brimming with carbon compounds like cosmic soot. While most stars fuse helium into oxygen and nitrogen, these aging giants defy expectations, dredging up carbon from their cores like miners unearthing buried diamonds. The result, a sky littered with glowing embers where carbon outnumbers oxygen, a chemical imbalance so extreme, it shouldn't exist under normal stellar physics. What makes NGC 6822's carbon stars so extraordinary isn't just their abundance, it's their defiance of the galactic rulebook. In larger galaxies like the Milky Way, carbon stars are fleeting phenomena, appearing only briefly as stars transition between life stages. But here, they dominate entire stellar neighborhoods, burning with longevity that challenges our models of stellar aging. Infrared observations reveal their atmospheres choked with molecules like cyanide and carbon monoxide, the stardust equivalent of a toxic fog. These aren't just dying stars, they're chemical factories forging the building blocks of future planets and possibly even life in their outer layers. The secret lies in their birth conditions. NGC 6822's metal poor environment, a relic of its primordial origins, creates stars with thinner outer envelopes. As they age, convection currents plunge deeper into their cores, hauling carbon to the surface with freakish efficiency. It's like stirring a pot of soup and discovering the spoon reaches all the way to the bottom, bringing up ingredients that should stay hidden. This process, called dredge up, happens more aggressively here than anywhere else in the local group, turning entire stellar populations into carbon-rich anomalies. But the real revelation is what these stars leave behind. When they finally shed their outer layers, they'll seed the galaxy with carbon-rich dust, the raw material for future solar systems. In a twist of cosmic irony, these aging giants might be the reason NGC 6822's next generation of stars could form planets with carbon-based chemistry eerily similar to Earth's. Their soot will become the bedrock of new worlds, their toxicity the precursor to possibility. Yet the mystery deepens when we compare them to carbon stars elsewhere. In most galaxies, these stars flicker out quickly, their carbon obscured by oxygen-rich neighbors. But in NGC 6822, they persist, burning for millennia with a consistency that suggests something unique about the galaxy's gravitational environment. Some theorists speculate its loose structure, lacking the dense spiral arms of larger galaxies, allows carbon stars to avoid the collisions and disruptions that normally cut their lives short. Others propose its slow star-forming pace gives these giants the solitude they need to age undisturbed, like centenarians in a quiet village. Ultimately, NGC 6822's carbon stars are more than cosmic oddities, they're time capsules. Their unusual chemistry preserves a record of how the early universe's stars enriched their surroundings, offering a glimpse into an era when carbon was rarer than gold. And as we study their flickering light, we're not just observing stellar evolution, we're witnessing the universe's unending quest to turn simplicity into complexity, one carbon atom at a time. The Aquarius dwarf galaxy appears to be unraveling in real time, its outer edges fraying into a shimmering arc of young, blue stars that stretch tens of thousands of light years into the void. Dubbed the Blue Plume, this celestial ribbon shouldn't exist. Dwarf galaxies like Aquarius are supposed to be ancient, their star-forming days long behind them. Yet here, against the darkness, gleams a trail of stellar newborns, their brilliance defying every expectation of how small, isolated galaxies behave. What makes this plume so baffling isn't just its youth, it's the precision of its formation. Unlike the chaotic debris left by galactic collisions, the Blue Plume stars move in eerie unison, streaming backward along Aquarius's orbital path like breadcrumbs marking its journey through the Milky Way's gravitational field. Spectroscopic analysis reveals these stars share nearly identical velocities and chemical compositions, a fingerprint suggesting they weren't torn away randomly, but liberated in a single dramatic event. It's as if the dwarf galaxy coughed up an entire generation of stars in one violent exhale. The likely culprit, a close encounter with the Milky Way's dark matter halo. As Aquarius orbits our galaxy, simulations suggest it may have dipped too deep into the invisible web of our halo's gravity, triggering tidal forces powerful enough to strip away its outer gas and stars. But here's the twist. The plume stars aren't just scattered survivors, they're actively forming new clusters as they drift away. This implies Aquarius didn't just lose stars, it lost the very gas that should have fueled future generations, birthing these blue stragglers in the process. Even stranger, the plume's chemistry defies typical galactic stripping. Its stars are richer in heavy elements than Aquarius's core, hinting they originated near the dwarf's center, where supernova once enriched the gas with metals. How did these metal-rich stars end up so far out? One theory proposes a slingshot effect. Aquarius's own gravity might have flung them outward during the Milky Way's tidal disruption, like marbles launched from a spinning plate. Alternatively, the plume could be the remnants of a smaller galaxy Aquarius cannibalized long ago, its stars now being pulled free by the Milky Way's interference. The implications ripple far beyond this one dwarf galaxy. The Blue Plume offers a rare chance to study tidal stripping in action, a process usually glimpsed only in simulations or the fossilized trails of long-dead galaxies. By tracking its stars, we're witnessing how galaxies like Aquarius contribute to the Milky Way's halo, their stolen stars gradually assimilated into our galaxy's outer fringes. It's a slow-motion dismantling, a preview of what may eventually happen to all the Milky Way satellites. Yet the most tantalizing question remains, could the plume be a lifeline, not a death sentence? Some models suggest the same tidal forces tearing Aquarius apart might be compressing its remaining gas, triggering sporadic star formation even as the galaxy disintegrates. If true, the blue plume isn't just a farewell, it's a defiant final act, proof that even in destruction, the cosmos finds ways to create. And as we watch this stellar ribbon fade into the Milky Way's embrace, we're reminded that gravity doesn't just tear things apart, it weaves them into something new. The Sagittarius dwarf galaxy isn't just fading into the Milky Way's embrace, it's being unraveled in spectacular fashion. Its stars strewn across the night sky in vast, shimmering rivers of light. These aren't random scatterings, they're tidal debris, a cosmic crime scene tracing billions of years of gravitational theft. As the Milky Way's gravity tugs and twists its smaller companion, stars once bound to Sagittarius are ripped away, forming sprawling streams that wrap around our galaxy like celestial spider silk. The sheer scale is staggering. These trails span over 1 million light-years, looping above and below the galactic plane in a dance of destruction and rebirth. What makes these stellar rivers so extraordinary is their structure. Unlike the messy splatter of a typical collision, Sagittarius's debris has sorted itself with eerie precision. Older, metal-poor stars from the dwarf's outer layers form one distinct stream, while younger, slightly richer stars trace a separate path like ingredients in a centrifuge separating by density. This isn't just random chaos, it's gravity's fingerprint, revealing how the Milky Way's tides have peeled Sagittarius apart layer by layer. Imagine an onion being unspooled in zero gravity, each concentric ring floating away intact. That's the level of forensic detail etched into these trails, but the real revelation lies in their motion. These stars aren't just passively drifting, they're marching in lockstep, their orbits synchronized by the Milky Way's pull. Astronomers have mapped their paths with such accuracy that they can rewind the cosmic clock, tracing each stream back to specific moments when Sagittarius swung too close to our galaxy's core. The debris doesn't just mark where the dwarf has been, it encodes the Milky Way's gravitational history, a record of how our galaxy's dark matter halo has shaped its surroundings over time. The most astonishing feature, the trailing and leading arms. As Sagittarius orbits, stars stripped from its front, the leading arm, race ahead, while those torn from behind the trailing arm lag like celestial breadcrumbs. Normally, these arms should mirror each other, but Sagittarius's trailing stream is far more massive, a lopsidedness that hints at a dramatic past. Some researchers suggest this imbalance means the dwarf once carried much more dark matter, which skewed the stripping process. Others propose the Milky Way's own halo is lumpier than we thought, its uneven gravity tugging harder on one side of Sagittarius than the other. Then there's the ghosts within the streams. Hidden among the tidal debris are dense knots of stars, not random clumps, but the remnants of globular clusters and dwarf galaxies once orbiting Sagittarius, now liberated into the Milky Way's halo. These clusters act like cosmic driftwood, their survival proving that galactic cannibalism isn't just about tearing things apart, it's about absorption, recycling, and transformation. The implications are profound. Sagittarius's debris isn't just stellar confetti, it's the blueprint for how galaxies grow. Every star added to the Milky Way's halo from these streams changes our galaxy's chemical makeup, enriching it with elements forged in another system entirely. We're witnessing a cosmic version of continental drift, where entire galaxies are dismantled and repurposed, their remains becoming part of something larger. And here's the kicker, this process isn't over. Sagittarius's core still orbits the Milky Way, destined to lose more stars with each pass. One day, it will vanish entirely, its identity erased. But its legacy will endure in these streams, a billion-year testament to the fact that in the cosmos, nothing truly ends, it just becomes part of the next story. The Canis Major dwarf galaxy has been at the center of one of astronomy's most heated debates. Is it truly a dwarf galaxy being devoured by the Milky Way, or just an illusion, a ripple in our own galaxy's structure masquerading as a separate entity? The controversy hinges on a single shimmering feature, the Monoceros ring, a sprawling arc of stars wrapping around the Milky Way's outer disk like a celestial serpent. To some, this ring is the smoking gun of a galactic merger, the torn-apart remnants of a once independent galaxy. To others, it's nothing more than a warped section of the Milky Way's own spiral arm, twisted into this unusual shape by ancient gravitational disturbances. Proponents of the dwarf galaxy theory point to the stars themselves. The Monoceros ring's stellar population carries distinct chemical signatures, lower metallicity, different abundance patterns, that align more closely with known dwarf galaxies than with the Milky Way's disk. These stars move in coordinated orbits, tracing paths that suggest they were yanked from a smaller system during a close encounter. Even more compelling, infrared surveys reveal a dense knot of stars near the constellation Canis Major, a potential surviving core of the original galaxy, clinging to existence amid the tidal wreckage. If confirmed, this would make the Canis Major dwarf the closest known galaxy to Earth, its corpse strewn across our skies like cosmic graffiti. But skeptics have a compelling counterargument. The Milky Way isn't a perfect static disk. Its outer edges warp and ripple, bending upward in some regions and downward in others, a consequence of past collisions with smaller galaxies or dark matter clumps. Computer simulations show these gravitational disturbances can produce structures eerily similar to the Monoceros ring. No dwarf galaxy required. The ring stars might simply be Milky Way natives, flung into this odd arrangement by the same forces that make our galaxy's disk resemble a slightly crumpled vinyl record. The debate takes a surreal turn when dark matter enters the picture. If the Canis Major dwarf is real, its dark matter halo should have left subtle gravitational fingerprints, telltale distortions in the Milky Way's outer gas clouds or stellar streams. Yet searches for these signatures have been inconclusive, leaving a gap in the merger theory. Conversely, if the ring is purely a Milky Way feature, why does it host star clusters with ages and chemistries that don't match our galaxy's typical disk populations? The most tantalizing clue might lie in the future, not the past. Upcoming telescopes like the Vera Rubin Observatory could settle the debate by mapping the motions of millions of stars in unprecedented detail. If the Monoceros ring stars all move in ways distinct from the Milky Way's disk, it's game over for the illusion theory. But if their motions blend seamlessly, the Canis Major dwarf might fade from the textbooks, demoted to a mere ripple in our galaxy's vast anatomy. What's at stake isn't just the classification of one faint smudge of light, it's our understanding of how galaxies grow. If the Canis Major dwarf is real, it's a living example of galactic cannibalism happening right in our backyard. If it's an illusion, it's proof of how little we still know about the Milky Way's own turbulent history. Either way, this cosmic whodunit reminds us that even the closest corners of the universe can harbor mysteries that defy easy answers. The Andromeda galaxy, our closest cosmic neighbor, hides a secret in its halo, a vast, shimmering arc of stars stretching over 200,000 light-years, a ghostly remnant of a galactic massacre. This colossal stellar stream, woven from the shredded remains of a devoured dwarf galaxy, glides through space like an ancient scar, preserving the violent history of Andromeda's expansion. Unlike the neat, symmetrical spirals we associate with galaxies, this structure is chaotic, a river of stars flung outward by gravitational forces so powerful they tore an entire galaxy apart. What makes this stream so extraordinary isn't just its size. It's the forensic detail etched into its stellar population. Each star in this river carries chemical fingerprints linking it to the same doomed dwarf galaxy, a system roughly 100 times smaller than Andromeda. Spectroscopic studies reveal these stars are rich in alpha elements: oxygen, magnesium, silicon, the telltale debris of rapid supernova explosions. This suggests the original dwarf was a prolific star factory, its brief, fiery life cut short when it ventured too close to Andromeda's gravitational maw. The stream's curved shape acts like a cosmic clock, tracing the precise path of the dwarf's final orbits before disintegration. But the real puzzle lies in the stream's structure. Unlike the scattered debris of other galactic collisions, this arc remains coherent, its stars moving in eerie unison. Computer simulations suggest Andromeda's dark matter halo played puppeteer, its invisible tendrils shepherding the stream into this exact configuration over billions of years. The stars didn't just scatter randomly, they were funneled, sorted, and arranged by forces we can't see. Some researchers even propose the stream's density variations could map the distribution of Andromeda's dark matter, offering clues about the galaxy's hidden scaffolding. Then there's the mystery of timing. Based on the stream's dispersal, the dwarf galaxy was likely consumed between 7 and 10 billion years ago, an era when Andromeda was still assembling itself. This makes the stream a fossil from the universe's adolescence, a relic from when galaxies grew by devouring their smaller neighbors. Yet its stars aren't uniformly ancient pockets of younger, bluer stars suggest the dwarf kept forming new stars even as it was being torn apart, a final burst of creation amid destruction. The implications stretch beyond Andromeda. This stream is a preview of the Milky Way's fate billions of years from now. When our galaxy collides with Andromeda, similar stellar rivers will weave through the merged supergalaxy. By studying this structure, we're glimpsing the life cycle of galaxies, not just how they grow, but how they digest. Every star in that shimmering arc is a monument to the universe's unrelenting appetite, a reminder that even the grandest spirals are built on the bones of the small. The Triangulum galaxy, or M33, spins gracefully in the local group with one glaring omission. Where are its satellites? Unlike the Milky Way and Andromeda, which are each orbited by dozens of dwarf galaxies, Triangulum appears bizarrely lonely, its cosmic neighborhood suspiciously empty. This absence isn't just a curiosity, it's a full-blown cosmological contradiction. According to our most trusted models of galaxy formation, a spiral as massive as Triangulum should have at least 10 to 15 dwarf companions tagging along, their gravitational dance shaping the larger galaxy's evolution. Yet observations reveal fewer than 5 confirmed satellites, and even those are so faint they barely register against the cosmic backdrop. This cosmic solitude raises a fundamental question. Is Triangulum an exception to the rules, or are our models missing something critical? One possibility is that its satellites exist but have eluded detection. Dwarf galaxies are notoriously dim, and Triangulum's location, positioned against the crowded plane of the Milky Way's disk, makes spotting them like trying to find fireflies in front of a floodlight. Recent deep sky surveys have uncovered a handful of ultra-faint candidates, but even if confirmed, their numbers still fall far short of predictions. The leading theory suggests Triangulum's satellites might have been torn apart long ago by its larger neighbors, their stars scattered into invisible streams. Andromeda's immense gravity could have acted like a cosmic thresher, stripping away Triangulum's retinue over billions of years of close encounters, but here's where the mystery deepens. Computer simulations show that even after such disruptions, traces of these dwarfs should linger either as stellar streams or orphaned star clusters. Yet Triangulum's outskirts are eerily clean, lacking the telltale debris fields seen around the Milky Way and Andromeda. This could imply its satellites were never there to begin with. Perhaps Triangulum formed in an unusually sparse pocket of the early universe where dark matter, the invisible scaffold that births dwarf galaxies, was in short supply. Without enough dark matter to clump into smaller structures, Triangulum's satellite system might have been stillborn. Then there's the wild card. What if Triangulum's missing dwarfs aren't missing at all, but hiding in plain sight? Some astronomers propose that its satellites could be masquerading as globular clusters, dense balls of stars often mistaken for tiny galaxies. A few of Triangulum's known globulars have odd chemical compositions and extended structures, hinting they might be the stripped cores of former dwarfs. If true, it would mean we've been overlooking Triangulum's satellites all along, their true nature disguised by cosmic camouflage. The implications stretch beyond Triangulum itself. If our models can't explain its lack of satellites, what does that say about our understanding of galaxy formation? Are we overestimating how many dwarfs should exist, or underestimating the violence of galactic interactions? Every observation peels back another layer, revealing that even in our own local group, the universe still has secrets to spill. And as we search for Triangulum's absent companions, we're forced to confront an unsettling possibility. Maybe the rules we've written for the cosmos aren't as universal as we thought. The large Magellanic Cloud's central bar isn't just a static structure, it's a cosmic engine, warping the rules of star formation in ways that defy expectations. Unlike the rigid, symmetrical bars found in spiral galaxies like the Milky Way, this one crackles with instability, its shape twisting and buckling under gravitational forces that should, by all accounts, tear it apart. Yet instead of collapsing into chaos, this turbulence has become a stellar nursery unlike any other, birthing stars at rates and in patterns that leave astronomers both fascinated and baffled. At the heart of the mystery lies the bar's unique geometry. Most galactic bars act like conveyor belts, funneling gas toward the center to fuel star formation in predictable bursts. But the LMC's bar behaves more like a malfunctioning pump, jammed, shuddering, and sporadically spurting gas outward into its surroundings. Infrared observations reveal pockets of intense starbirth not just along the bar's length, but in bizarre, off-axis clusters that seem to erupt wherever the structure's gravitational tides fray the hardest. It's as if the bar isn't guiding star formation so much as electrocuting it into existence, sending jolts of activity flaring up in random directions. The culprit, a dance of dark matter and dynamical friction. Simulations suggest the LMC's bar isn't anchored firmly to the galaxy's core, but instead wobbles like a spinning top losing momentum, its rotation gradually slipping out of sync with the surrounding disk. This misalignment generates shock waves that ripple through the bar's gas clouds, compressing them into knots dense enough to ignite stars. The result is a starburst pattern that looks less like an assembly line and more like popcorn popping, erratic, uneven, and impossible to predict. Yet the most striking evidence of this instability lies in the bar's metallicity gradients. Normally, bars homogenize their gas, mixing it thoroughly as they rotate. But the LMC's bar hosts stark chemical disparities, with younger, metal-rich stars clustered along its western edge and older, pristine populations clinging to the east. This suggests the bar isn't just unstable, it's leaking, hemorrhaging freshly enriched gas from one side while drawing in primordial fuel from the other. The implications are staggering. This isn't a closed system, but a broken valve, cycling material in lopsided bursts that leave their mark on every newborn star. What makes this phenomenon so valuable isn't just its strangeness, it's its rarity. The LMC offers a once-in-a-local universe chance to study a bar in the throes of dissolution, a process normally observable only in computer simulations. By decoding its chaos, we're glimpsing the fragility of galactic structures, the fine line between order and bedlam that shapes how galaxies evolve. And as we watch this cosmic bar tremble under its own weight, we're reminded that even the grandest architectures of the universe are never truly permanent, just momentarily balanced between collapse and rebirth. Stretching like a cosmic umbilical cord between two galactic siblings, the 75,000 light-year-long gas bridge linking the small Magellanic Cloud to its larger neighbor isn't just a filament of hydrogen, it's a celestial crime scene, revealing the aftermath of a gravitational heist that's been unfolding for nearly 2 billion years. This ethereal tether, composed mostly of ionized hydrogen and sparse stellar populations, glows faintly against the intergalactic darkness, its very existence defying expectations about how small galaxies interact. Most satellite galaxies like the SMC are stripped of their gas entirely when venturing too close to larger companions. But here, instead of total destruction, we see a delicate balance. Gravity's fingerprints preserving a fragile connection even as it tears the smaller galaxy apart. What makes this bridge so extraordinary isn't just its scale, though spanning nearly the distance between Earth and the large Magellanic Cloud is staggering, but its dual nature. On one hand, it acts as a lifeline, funneling gas from the SMC toward the LMC in a slow-motion transfusion that's fueling star formation in its larger neighbor. On the other, it's a testament to violence, a structure born from the tidal forces that have warped both galaxies like taffy pulled between unseen hands. Radio telescopes reveal the bridge's gas is clumped into dense knots, each one a potential seed for future stars, while infrared observations show trails of dust weaving through it like cosmic breadcrumbs, evidence of the SMC's gradual disintegration. Yet the real enigma lies in the bridge's asymmetry. Unlike the neat, arching tidal tails seen in other galactic collisions, this structure is lopsided, with more gas stretching toward the LMC than trailing behind the SMC. This imbalance suggests the bridge isn't just passive debris, it's actively being siphoned, as if the LMC has inserted a gravitational straw into its smaller companion. Even stranger, parts of the bridge appear to be collapsing inward, forming isolated star clusters that defy the usual rules of stellar birth. Normally, gas this diffuse shouldn't coalesce into stars, yet here they are, stellar infants flickering to life in the cosmic void, far from any traditional galactic nursery. The bridge's most tantalizing secret, though, might be its role in the local group's larger dynamics. Simulations suggest it's not just connecting the SMC and LMC, it's part of a vast, invisible conveyor belt of gas that's been cycling material between the Magellanic Clouds and the Milky Way for eons. Some of this gas may eventually reach our galaxy, contributing to the reservoir that fuels star formation in the Milky Way's outer disk. It's a humbling thought. The faint glow of this bridge isn't just a local curiosity. It's a thread in the grand tapestry of galactic evolution, a reminder that even the most distant structures are part of an interconnected cosmic web. And so, this fragile bridge stands as both a bond and a boundary, a testament to the delicate dance of destruction and creation that shapes the universe. As we trace its faint outline across the sky, we're not just mapping gas, we're witnessing the slow, beautiful unraveling of a galaxy and the birth of something new from the fragments it leaves behind. From Andromeda's lopsided dark matter halo to the large Magellanic Cloud's chaotic star-forming bar, the local group is packed with cosmic oddities that defy every textbook. These 50 strange objects aren't just quirks, they're revolutionary. The Sculptor dwarf, with its eerie dark matter dominance, forces us to rethink how galaxies hold themselves together. The Phoenix dwarf's ghostly resurrection after billions of years of silence shatters assumptions about galactic life cycles. And let's not forget Antlia too, the galaxy that forgot to be a galaxy, a wispy, half-formed specter drifting through space like a cosmic afterthought. What makes these objects so thrilling isn't just their strangeness, it's how they expose the gaps in our understanding. Take the Triangulum galaxy's missing satellites. Why does this spiral, large enough to command an entourage of dwarf galaxies, float in such unsettling solitude? Or consider the Sagittarius Stream, a river of stolen starlight so vast it wraps around the Milky Way like a noose, whispering secrets about galactic cannibalism on a scale we're only beginning to grasp. Each anomaly is a crack in the facade of our cosmic knowledge, a reminder that even in our own celestial neighborhood, the universe delights in throwing curveballs. And that's the real wonder here. If we've uncovered this many mysteries in the local group alone, a speck of the observable universe, what else is out there just beyond our telescope's reach? Could there be galaxies made entirely of dark matter, invisible except for their gravitational pull? Might rogue black holes wander between stars, undetectable until they flex their gravity on unsuspecting worlds? The more we learn, the clearer it becomes. The universe isn't just stranger than we imagine, it's stranger than we can imagine. So what's your cosmic pet mystery? A bizarre object you've read about, or a space phenomenon that keeps you up at night? Drop your thoughts below, because the next great discovery might start with a curious mind and a wild idea. And who knows, maybe one day we'll revisit this list only to find it's grown twice as long, filled with new enigmas waiting to rewrite the rules all over again. After all, in a universe this unpredictable, the only